Hi friend, come on in, get settled, and if the space around you is already quiet, good, because that is exactly the mood tonight's story needs. I am glad you found your way here tonight, wherever here happens to be for you right now, because somewhere in the long story of this planet there is a single stretch of time, geologically speaking barely an afternoon, when the ocean simply stopped being a safe place to exist, not because of a monster rising out of the deep, not because a rock fell out of the sky. The water itself turned against nearly everything that called it home, and by the time it was over, 96 out of every 100 creatures in the sea were simply gone. Tonight, before we get anywhere near that ending, we are going back, all the way back, to the last quiet morning before any of it began. Now, if slow deep storytelling like this is something your evenings could use more of, tapping subscribe or dropping a like helps more than you would think, and sharing it with someone who could use a calmer night helps even more. Comments make my whole evening too, so tell me, where in the world are you tonight and what time is it? Where you're curled up right now, I look through every single one, I promise. All right. Dim the lights if you can, maybe let a fan hum softly somewhere in the background, and let us slip into the past together. 252 million years ago, there was only one continent on Earth. Every landmass we know today, all pressed together into one single sprawling shape geologists would later name Pangaea, and wrapped around that one continent was a single endless ocean. No Atlantic, no Pacific, just one enormous body of water stretching farther than anyone standing on its shore could possibly have imagined. If you could rise above it all for a moment, high enough to see the whole coastline stretching out beneath you, the land itself would barely register as land to us. Low tangled forests of ferns and early conifers roll toward the water. There is no grass yet anywhere on Earth, no flowers, nothing green and soft underfoot the way we're used to. Just rough plants, red soil, and a warm salty breeze drifting across a coastline that no human eye will ever get the chance to see for itself. Now picture a morning near the edge of that one continent, a shallow warm sea lit gold by a sun that looks almost exactly like ours, because it is ours just 252 million years younger. The water here is clear enough in most places to watch the bottom without ever needing to dive. And the bottom, my friend, is busy. This is not a coral reef in the way we picture reefs today. There are no bright orange branches, no clownfish darting between them. This reef is built by sponges, by crusted sheets of ancient algae, and by small cushion-shaped corals called rugose, and tabulate corals stacked together over thousands of years into a low, uneven wall of stone and life. It is quieter than a modern reef, slower, but it is no less alive. Fields of crinoids sway in the current like an underwater garden, thin stalks topped with feathery little arms sifting tiny scraps of food out of the passing water. Scientists who study fossils like these sometimes call them sea lilies, which is generous considering they are technically animals and not plants at all, but the name fits the picture better than the science does, so we will let that one slide. Spread across the seafloor, thousands of brachiopods sit inside small ribbed shells, looking from a short distance almost exactly like modern clams, though they are only distant cousins at best. They have carpeted seafloors like this one for hundreds of millions of years, already quietly without ever needing to be impressive about it. If the ocean gave out awards for reliability, brachiopods would have a shelf full of them by now. Above them, a handful of ammonoids drift through open water, their tightly coiled shells catching the light. One of them tightens for a moment, pulls in water, and pushes forward in a soft sudden burst, the same basic trick its distant descendants squid and octopus still rely on today. It is hunting something smaller than itself, something we would barely notice if we were floating right beside it, and within a few seconds the hunt is already finished. In this ocean, that is simply lunch. Nothing more dramatic than that. And somewhere down in the sand and broken shell fragments, moving slower than almost everything else in this scene, a trilobite goes about its morning. If you want to talk about seniority in the ocean, trilobites earned every bit of it. By this point in Earth's story, they had already been crawling across seafloors for nearly 300 million years, which means that compared to them, almost everything else in this picture is a newcomer. Human beings would not show up for another 250 million years after this exact morning. And even then we would spend most of our short history not even knowing trilobites had existed at all. Here is the quiet detail most people would miss, though, if they were only watching this scene and not really looking at it. By this particular morning, there are only a couple of trilobite species left swimming anywhere in the ocean. The great trilobite dynasty, thousands of species deep at its peak, has already worn itself down to almost nothing. Not from any disaster yet, just from the slow, ordinary churn of time, the same churn that eventually catches up with every dynasty in the ocean or otherwise. The trilobite does not know any of that, of course. As far as it is concerned, this is simply another Tuesday. There is sand to sift through, and that is about as complicated as its plans get. Not far from it, tucked into a crack between two rocks, a eurypterid waits without moving. People sometimes call these creatures sea scorpions, though they are not scorpions at all, just distant armoured relatives of crabs and spiders that have been ambushing prey in oceans like this one for almost as long as the trilobites have been crawling through them. Their family too is quietly running out of road, though nothing in this particular moment gives that away. It simply looks like an old patient hunter doing what old patient hunters do. Farther out past the reef, something larger moves through open water with the kind of unhurried confidence you only get once you've outlasted almost everything else on the planet. A shark cruising low, sensing the smallest vibrations in the water, the way its family always has. Sharks were already old news by this point in Earth's story, and whatever it is that lets them keep surviving one catastrophe after another, it is already working exactly as advertised long before anyone is around to write it down. Tiny organisms called fusulinids drift everywhere in the water column, too smaller than a single grain of rice, so easy to overlook completely. Except there are so unbelievably many of them that hundreds of millions of years from now, entire cliffs of limestone will turn out to be built almost entirely from their tiny shells. Which, if you sit with that for a second, might be the most understated retirement plan in the whole history of life on Earth. None of this looks like the opening scene of a disaster. It looks like an ordinary shift at the bottom of an ordinary sea in a world that has been running roughly this way for longer than most of us can comfortably picture. Warm water, slow currents, creatures going through routines that in one form or another had already been repeating themselves for tens of millions of years. And that more than anything is what makes this particular morning worth sitting with for a moment. Because as far as any creature down here could tell, this was simply how the world worked. This was how it had always worked, and reasonably this was how it would keep working tomorrow and the day after that and every ordinary day beyond it. There was no warning written across the sky, no tremor in the sand that anything down here could feel yet. Just warm water, soft light, and small ordinary creatures carrying on exactly as they always had. If this reef made a sound, it probably would not be dramatic at all. Just the soft clatter of shell against shell, the faint hiss of current moving through coral, the occasional muffled thud of something small being eaten by something slightly less small. A calm sound. A background sound. The kind you would stop noticing within a minute of hearing it. The same way you eventually stop noticing a fan humming in your own room at night. It is in its own strange way a little bit like any ordinary morning any of us have ever had. The kind where nothing about the coffee or the drive or the weather outside gives the smallest hint that everything is about to change. Most of us have a morning like that somewhere in our past, one we only recognize afterward, looking back as the last normal day before everything else. We rarely get warnings before the mornings that end up mattering the most. Neither did they. And maybe that is the part of this story worth holding on to a little longer than the rest before we go anywhere near what happens next. This ocean had already been doing the exact same thing in roughly the exact same way for tens of millions of years. Stability like that has a way of feeling permanent, almost boring, right up until the moment it stops being either one. But thousands of miles north of this reef, in a part of the world that does not yet exist as a shape on any map, something else is happening. Up there, the coastline gives way to dry forest, and the dry forest eventually gives way to open, empty ground, the kind of landscape that looks like nothing is happening on it at all. A few early reptiles move slowly through the underbrush, hunting insects, minding their own business, utterly unaware that they happen to be standing on top of the single, most dangerous piece of ground on the entire planet, because far beneath their feet, miles down past soil and rock and older rock, still heat has been gathering for a very long time already. Quietly, patiently, the way pressure almost always gathers right before it stops being patient. Somewhere down there, rock is no longer entirely rock. It has started to soften, then thin, then rise inch by unbearably slow inch, the way anything does when it has finally been pushed past what it can hold. It has not broken through yet, but it will not stay hidden much longer. So while our trilobite finishes its unremarkable Tuesday, and the crinoids keep swaying and that shark keeps cruising past like it owns the place, it is probably worth going to take a look at what is building underneath all of it. Because to really understand what was about to happen to this ocean, we cannot stay here on this one reef as peaceful as it is. We have to pull back far enough to see the whole shape of the world as it existed back then. Because as it turns out, the very shape of that world had already set a trap long before a single volcano ever erupted. So let's sit with that trap for a moment, because it did not appear overnight, and it did not begin with anything that looked even remotely dangerous. For nearly 200 million years before our reef ever existed, the pieces of this puzzle had been drifting toward each other, an inch or two at a time, the way continents always move, which is to say slower than anything a human eye could ever stay patient enough to watch. If continental drift had a highlight reel, it would be the least exciting footage in the history of the medium 1 inch of movement stretched across an entire human lifetime, repeated several hundred times in a row. One by one, ancient landmasses that geologists now call Gondwana and Laurussia pressed into each other, crumpling the ground between them into brand new mountain ranges as they went. If you have ever stood somewhere in the Appalachian Mountains on a ridge in Tennessee or Pennsylvania, or upstate New York worn soft and green with age, you have literally stood on the scar tissue from that collision. Those mountains were once as sharp and towering as the Rockies are today. Time and a few 100 million years of rain sanded them down into the gentle shape so many of us grew up hiking without ever knowing what they used to be. On the far side of that same slow collision, something similar was happening to a very different stretch of ground, the block of land that would one day be called Siberia. It welded itself onto the rest of the growing supercontinent along a seam that pushed up its own mountain range, one we still call the Urals today, a border so old and so thoroughly worn down now that most people crossing it have no idea they are walking over the stitching that once held two separate worlds together. Hang on to that name for a moment. We are going to be coming back to it. By the time our morning on that reef was happening, all of that drifting and crumpling had finally finished. Every major landmass on Earth had locked together into a single continent, and that continent, once fully assembled, quietly rewrote the rules for everything living in the ocean around it. Here is the part most retellings of this story tend to skip past. Almost all ocean life then and now is packed into a surprisingly thin ring of shallow water, hugging the edges of continents. Not the open ocean, not the deep, dark middle of it. The edges. Sunlight reaches the bottom there. Nutrients wash in from the land nearby. It is in every sense that matters to a living creature the richest real estate the ocean has ever offered. If that sounds a little abstract, think about coral reefs in our own time. Reefs take up a remarkably tiny sliver of the ocean floor worldwide, and yet they are home to an outsized share of everything that swims, crawls or hides in salt water. Shrink that sliver even by a little, and you're not just losing a few corners of habitat here and there. You're pulling the floor out from under a wildly disproportionate amount of life all at once. Now stretch that same idea across the entire planet, not to one reef system, but to almost every stretch of shallow coastline that existed anywhere on Earth, all shrinking at roughly the same time. When every continent on the planet fuses into one enormous shape, something fairly obvious happens to that ring of shallow water. It shrinks dramatically. All that coastline, all that prime sunlit real estate that used to exist along the edges of several separate land masses collapses down into the edges of just one. Entire neighborhoods of ocean life, the rough equivalent of whole coastal cities, simply stopped existing. Not because anything hunted them down or attacked them directly, but because the ground underneath them was no longer there to build a life on. And it gets quieter still in a way most people never think to ask about. With one solid mass of land stretching from near one pole to near the other, the cold oxygen-rich water that normally sinks near the poles and creeps along the sea floor toward the tropics suddenly had a much harder path to travel. Less of that cold water made it through. Less oxygen travelled with it. The warm, shallow water still clinging to the edges of this new supercontinent was quietly already starting to run a little short of breath years before anything with a name like Siberia ever entered this particular story. Picture it a little like the heating system in an old house, the kind with a radiator in every room, all fed by pipes running back to one furnace tucked away in the basement. Block enough of those pipes, or make the route long and tangled enough, and some rooms stop getting warm no matter how hard that furnace works. The ocean circulation ran on a similar idea, just in reverse, carrying cold oxygen-rich water instead of heat. Wrap most of the planet in one unbroken landmass, and some rooms of that ocean simply stopped getting what they needed through absolutely no fault of the furnace at all. Now I want to pause on something here because it would be easy at this point to assume that the shrinking coastlines and the thinning oxygen were themselves the disaster we're building toward. Some of the earliest research into this extinction leaned pretty heavily in that direction. But scientists who have gone back through the numbers far more carefully since then, lining up the exact timing of Pangaea's assembly against the actual moment everything collapsed, have mostly ruled that idea out as the main event. The supercontinent alone did not wipe out 96% of ocean life. It could not have. Continents had drifted together before earlier in Earth's much older history, without anything resembling this scale of collapse following behind them. There is an even more specific wrinkle here too, if you want the honest, slightly messier version of this story instead of the tidy one. The old assumption used to be fairly simple. Less habitat automatically means fewer species in something resembling a straight line. But when researchers tested that assumption against other better documented stretches of Earth's history, the straight line mostly refused to hold up. Losing habitat on its own, it turns out, rarely explains a collapse this severe, which means something else had to be doing most of the actual damage. Geography loaded the gun, in other words. It did not fire it. I find that distinction oddly comforting in a strange sort of way, even though nothing about this story is especially comforting. It means the Permian Ocean was not simply doomed by its own address. Millions of years of evolution had built creatures perfectly capable of adjusting to a shrinking coastline given enough time to do it in. Species had weathered shifting shorelines before adapted to new neighbours, as separate oceans merged into one learned to share crowded reefs without collapsing entirely. What this ocean could not survive was a shrinking coastline and thinning oxygen and dropping sea levels all stacking up at once with absolutely no time left over to adjust to any of it before the next blow landed. Historians studying the fall of entire human civilizations run into a similar argument more often than you might expect. It is tempting looking back at any collapse to reach for one single tidy cause: a war, a famine, one bad decision by one powerful person. But the historians who study these collapses most carefully tend to land in roughly the same place. The paleontologists have landed here. It is almost never one clean blow. It is drought stacked on top of trade routes already failing, stacked on top of a government already stretched too thin to respond to either. Take away any single layer, and the whole structure might have held. Stack them all together in the wrong order at the wrong time, and even a fairly ordinary shock becomes the one that finally brings everything down. So if the supercontinent was not the killer, what exactly was it? I would argue it was something more like a setup. Think about the last time you got sick right after a stretch of bad sleep, or a particularly rough month, or one too many skipped meals in a row. The cold you caught was still technically what put you flat on your back, but it hit as hard as it did because your body had already been quietly running on empty for weeks beforehand, long before that first sniffle ever showed up. Pangaea was the empty tank. It did not pull the trigger on anything. It simply made sure that whatever eventually did pull it would not have to work very hard to finish the job. Or think of it a different way if that one does not quite land for you. A rainy day fund only matters on the actual day it rains. Right up until then, an empty one looks exactly the same as a full one sitting quietly in a drawer, somewhere never asked to prove a thing. In a very real sense, Pangaea had already spent this ocean's rainy day fund decades before the clouds ever showed up on the horizon, and nothing swimming through these waters had the faintest idea the account was already running low. Have you ever noticed how the moments that actually break us are rarely the first blow? More often they're the fifth one or the sixth, stacked quietly on top of every earlier one nobody thought to add up at the time. I think that is exactly what was happening to this ocean long before it had any obvious reason to worry. Because the geography was not even finished making things harder yet. Long before the events we're building towards sea levels around the world had already dropped several separate times throughout the Permian Period, each time draining a little more of that already shrinking shallow water away completely. Geologists who study the layered rock from this era can actually count these drops almost like tree rings, each one marking a stretch of time when the ocean pulled back from the land and the living space for shallow water creatures shrank a bit further than it had the time before. By the time we reached the final chapter of the Permian, the ocean had already been dealt a fairly rough hand, and not one drop of lava had even reached the surface yet anywhere on the planet. The single land mass was reshaping the climate on land too in ways that rarely make it into the retelling of this particular story. With so much of Pangaea's interior sitting hundreds of miles from any coastline, the moisture that usually drifts in off the ocean and waters everything nearby never made it that far inland. Vast stretches of the continent's centre dried into desert, some of the harshest, most extreme desert Earth had produced up to that point in its history, scorching by day and bitterly cold by night, with almost nothing gentle in between. Ever wonder how much of a coastline's fate can depend on things happening 1,000 miles inland, in places the water itself never even touches? This might be one of the clearest examples there is. It is worth holding on to if only because it tells us the ocean was never the only part of this world, already under quiet strain well before the real trouble arrived. None of this, by the way, was the least bit obvious to the crinoids swaying gently in the current back on our reef, or to that trilobite still sifting patiently through the sand. From where they were sitting, the world still looked whole. Honestly, it still looked remarkably normal, the same as it had for longer than any of them could have measured, even if they had the means to try. Their whole understanding of what normal even meant had been shaped entirely by an ocean that was in secret already several stacked misfortunes deep. And maybe that's worth sitting with for a second, because it is rarely the big dramatic wound that takes a system down on its own. More often it's the slow accumulation of smaller, quieter ones stacking up beneath the surface, waiting for one more push to finally show themselves. And that push, as it happens, was already on its way. Remember that heat we left gathering under the ground thousands of miles north of our reef, patient and quiet and completely out of sight? It had not gone anywhere while we were busy talking about coastlines and currents and empty tanks. If anything, it has been building the entire time, inch by inch, nearer to the surface, utterly indifferent to whatever theories geologists millions of years from now would eventually come up with about shrinking habitats and thinning oxygen. It did not care about any of that. It had its own kind of momentum by this point, and it was quickly running out of places left to put it. Somewhere beneath that stretch of ground we mentioned a moment ago, the one stitched onto the rest of the supercontinent, along those old worn-down mountains, rock that had stayed solid for hundreds of millions of years was beginning to behave like something else entirely. Because underneath all of the slow, patient vulnerability we just walked through together, something else was finally about to force its way out into the open, and once it did, it would not stay quiet or patient or contained ever again. What finally broke through when it broke through did not look anything like the volcanoes most of us picture when we hear that word. There was no single mountain involved. No neat cone-shaped peak quietly building toward one dramatic moment before letting go. What happened across that stretch of northern ground was stranger than that, and honestly more unsettling too. The ground itself simply began to split open along cracks stretching for miles in more than one place at once, and instead of one eruption, the region produced what geologists now call a flood basalt, an event so enormous it barely resembles a volcano at all in the way we normally use that word. It resembles something more like the planet bleeding. Try picturing it for a moment, not as a chart or a statistic, but as something a person could have stood far enough away to actually watch, assuming there had been anyone around yet capable of watching. Rivers of glowing orange rock wider than any river we would recognize today, crawling forward across the land at a pace slow enough to outrun on foot, but wide enough and hot enough that outrunning it would have done a person very little good over any real distance. The air above these flows would have shimmered and warped with heat. At night, the entire horizon in that part of the world would have glowed a dull furnace, red bright enough in places to be mistaken for a second sickly sunset that never quite finished setting. Over the following stretch of time, something under 2 million years, which sounds like an eternity to us, but barely registers as a blink in the story of this planet, molten rock poured out of these cracks again and again, layer stacking on top of layer, until the total volume added up to somewhere around 3 million cubic kilometers of solid rock. Numbers that size rarely mean much on their own, so try this instead. If you gathered up every drop of that lava and poured it evenly across the ground, it would bury an area roughly half the size of the United States coast to coast, under a shell of solid stone. And here is the detail that took researchers a surprisingly long time to fully appreciate, the one that turns us from a very large volcanic event into something far more dangerous than a large volcanic event tends to be on its own. None of this happened in one clean continuous burst either. The traps did not simply switch on and stay on for 2 million years straight. They pulsed, quieted, and pulsed again in phases separated by stretches of relative calm that may have lasted centuries long enough for anything paying attention to have started hoping the worst was over, right before the ground split open somewhere new and proved it wrong. Siberia was not even acting entirely alone, as it turns out. A separate, somewhat smaller stretch of intense volcanic activity had already scarred a different corner of the world in what is now southwestern China in the millions of years right before this one. Some researchers studying that earlier event now suspect it may have already been quietly straining the planet's climate and ocean chemistry before Siberia ever properly got started, less like an independent disaster in its own right and more like an opening act. Nobody in the audience realised they should have been worried about. I like to think of it honestly less as one villain acting alone, and more as a planet that had been handed several loaded warnings in a row and simply failed to heed a single one of them in time. History, human or otherwise, rarely offers a lone cause standing by itself in an empty room. It usually offers a pile-up, and by the time anyone notices the pile-up for what it is, the moment for turning back has generally already passed. Not all of that molten rock ever reached the surface. A huge amount of it pushed sideways instead underground, forcing itself between existing layers of rock in flat spreading sheets that geologists call sills. And it just so happened, whether by dark coincidence or something resembling inevitability, that the ground sitting on top of this particular hotspot was packed with exactly the wrong material to have superheated rock shoved through it. Thick beds of ancient coal layers of buried salt and rock, soaked in trapped organic matter, the compressed remains of forests and swamps hundreds of millions of years older still. Picture shoving a lit torch not into empty air but directly into a warehouse stacked floor to ceiling with fuel. That is roughly what was happening, one slow, scalding intrusion at a time underneath the surface of what would one day be called Siberia. The heat did not just melt rock. It baked entire buried forests, cooking coal and oil-soaked sediment, the way a furnace cooks anything shoved inside it, releasing gas after gas after gas that had been sealed underground for longer than most of us can comfortably picture. Have you ever wondered what actually happens to a fossil fuel deposit that gets cooked rather than burned outright with no open flame anywhere near it? It turns out heat alone is more than enough. Squeezed and baked from underneath by intruding magma, these coal beds would have swelled with trapped gas, the same way bread dough swells with trapped air. Except here that gas had nowhere gentle to go. In places, the pressure built up faster than the ground could quietly release it, and the result was hundreds of small violent explosions blasting narrow pipes straight up through miles of rock, launching pulverized stone and ash into the sky in bursts that had almost nothing to do with lava at all. These do not function like the eruptions we usually picture. They function more like detonations. Think of shaking a bottle of soda for months on end, sealed the whole time, buried under a mile of solid rock, with absolutely no one around to relieve the pressure gradually. Eventually something has to give. In the Siberian Traps, hundreds of somethings gave scattered across the entire region, blasting debris and gas skyward in violent localized bursts that had far more in common with a bomb going off than with anything most of us picture when we hear the word volcano. Whatever came out of the ground during those years, whether it rose gently out of a lava flow or blasted upward through one of these explosion pipes, rarely came out alone. Carbon dioxide in volumes almost impossible to picture, sulfur dioxide choking and acidic, methane seeping up out of the cooked coal beds, and a strange, dangerous family of chlorine and bromine-bearing gases, similar in spirit to some of the very chemicals that would one day put a hole in this planet's ozone layer. This time coming not from a spray can in a factory somewhere, but straight out of ancient melted salt deposits buried underneath the traps. None of these gases showed any particular manners about where they intended to go either. Once loose in the atmosphere, they do not stay polite or local. They rise, spread, and drift across the entire globe indifferent to oceans, continents, or the quiet, unremarkable morning still unfolding on a reef thousands of miles away that had absolutely nothing to do with any of this. Geologists, for what it is worth, are not always the most dramatic namers of things. An event capable of burying half a continent under lava and cooking an entire coal basin from underneath earned itself the fairly modest title of a large igneous province, which is a perfectly accurate description, and also possibly the least frightening name ever handed to one of the worst events this planet has ever produced. For a long time, all of this was a strong suspicion, not a proven case. Earlier generations of scientists lined up plenty of circumstantial evidence, but circumstantial evidence, no matter how compelling, rarely settles an argument in an active field of science. Ever wonder how anyone puts a precise date on something that happened before there were calendars, before there was writing, before there was almost anything alive capable of remembering an event like this at all? This is roughly how. What finally tied everything together was a method almost embarrassingly simple to explain, even if the actual laboratory work behind it took years to complete. Buried within these volcanic rocks are tiny crystals called zircons, and zircons happen to trap a small amount of radioactive material inside themselves the moment they form material that decays at a rate so steady and so well understood that measuring what remains of it works a little like finding the exact timestamp sealed onto that crystal on the day it cooled. Researchers gathered zircons from the very beginning of the eruptions and from the very end of them, and lined those dates up directly against zircons pulled from rock layers, marking the extinction itself on the far side of the world in southern China. The dates matched tightly enough that there was very little room left for doubt. The eruptions did not happen sometime near the extinction. They happened during it, layered right on top of it, down to a level of precision that researchers involved in the work compare to catching a killer with the weapon still in hand, evidence about as direct as this particular field of science is ever likely to produce. It is worth pausing on this for a moment because plenty of people understandably mix this extinction up with the one that took out the dinosaurs and assume a rock falling out of the sky must have been involved here too. It was not. Scientists have gone looking for the kind of evidence a large impact tends to leave behind: unusual metals scattered in a telltale layer, shocked mineral grains, and an enormous crater somewhere on the globe waiting to be found. And after decades of searching, none of it has turned up in any convincing form. Whatever devastated this ocean came up from underneath the ground, not down from space, and honestly, there is something almost more unsettling about that. A falling rock is bad luck. A planet quietly assembling its own disaster, one buried coal seam at a time, is something else entirely. And the fingerprints do not stop at dates stamped onto a crystal either. Thousands of miles from Siberia in rock pulled out of the Arctic reaches of Canada, researchers have found unusual traces of nickel, chemically fingerprinted back to these very eruptions, carried there through the atmosphere, drifting across an entire hemisphere, before finally settling into mud that would one day become solid rock. Layers of ash from burned coal have turned up in that same distant rock. Even mercury and metal volcanoes are especially good at flinging into the sky in enormous quantities, shows up as a sharp spike in rock, laid down all over the planet at precisely this moment, like a signature left behind by a fire that finished burning hundreds of millions of years ago, and still somehow never quite stopped being detectable. Taken all together, it stopped being a reasonable question of whether Siberia was responsible for what happened next. It became a question of exactly how. It is strange to think that human industry in barely 2 centuries has already returned a meaningful fraction of carbon to the atmosphere. Through entirely different means, no volcanoes required, just factories, engines, and a great deal of fuel pulled up out of the ground on purpose rather than cooked out of it by underground accident. The comparison is not exact. The timescales and mechanisms involved are different enough that no serious scientist would call the two events identical twins, but it is part of why researchers keep returning to this particular chapter of the past again and again, treating it less like a finished history lesson sitting quietly on a shelf and more like a case study still worth studying carefully. Somewhere near the edge of all this, in that same dry country we passed through earlier, on our way north, the animals sharing that ground would have had no name for any of what was happening beneath their feet. Only smoke on a horizon that never fully cleared anymore. Ground that occasionally shuddered for no visible reason. A sky that more and more often carried a strange sour taste on the breeze, the kind of thing you might not think twice about the first few times right up until it stops going away. None of that stayed over Siberia for long, of course. Gas does not respect borders, and it certainly was not going to respect the width of an ocean. Every single thing released underground during those years, the carbon, the sulfur, the strange chlorine-laced fumes rising out of melted salt was about to spread. Not slowly either. Far faster than anyone standing on that quiet reef we started with could ever have gotten ready for. Somewhere above the water, the sky over that reef still looked ordinary for now. The sun still rose the same soft gold it always had. The crinoid still swayed, the trilobite still sifted its patch of sand, and the shark still cruised past with that same unbothered confidence because none of what was coming had actually arrived yet. But it was already moving, because the real question was never really whether this would reach the rest of the world. It obviously would. The real question, the one that would end up mattering most to every creature sharing this planet at the time, was how quickly. Fast, as it turns out, is a complicated word when you're talking about a planet instead of a person. To every creature alive on that reef, nothing was going to feel sudden at all. There would be no single morning where the water simply turned. What was coming would arrive the way most real disasters actually arrive, not as a single blow, but as a series of years, then decades, then centuries, each one slightly worse than the one before. It easy to explain away, individually, impossible to explain away, once you finally added them all together. And yet, by the standards of the planet itself, by the standards of a world that measures most of its changes in millions of years, what was about to happen here would count as something almost instant. Both of those things are true at once, and honestly, that tension is the whole reason scientists have spent decades fighting to pin an exact number on it. So let's talk about how they actually did that, because the story behind the number is nearly as remarkable as the number itself. There is a particular hillside in southern China in a place called Meishan that geologists eventually settled on as something like the planet's official reference copy for this entire event. Not because anything especially dramatic happened there at the time. It was simply a spot where the ocean floor had been quietly laying down thin, undisturbed layers of sediment for millions of years, one on top of another, largely undisturbed since like pages left completely untouched in an enormous stone book. When researchers finally cut into that hillside and started reading those pages in order, they realized they were looking at one of the cleanest, most complete records of this catastrophe found anywhere on Earth. Stand at the base of that hillside today, and you're looking at roughly 200 vertical feet of solid limestone, each thin layer, representing a slice of time far too long for any human calendar to properly hold. Scientists have since carved the whole exposure into more than 100 numbered beds, catalogued one at a time, the way you might number the pages of a book you were terrified of ever losing your place in. Here is a detail I happen to love and one most people have never heard. The official boundary separating the entire Permian period from the entire Triassic period, the line the whole scientific world formally agreed on, as the true end of one chapter of life on Earth and the beginning of the next, is not marked by ash or fire or anything dramatic at all. It is marked by the first appearance of a single tiny fossil, a small tooth-like structure from a nearly microscopic eel-shaped creature called a conodont. An organism smaller than a grain of rice ended up essentially by committee vote among scientists more than a century later, as the final punctuation mark on the deadliest event this planet has ever produced. Scientists, it turns out, can be every bit as particular about their paperwork as anyone filling out a form at the license office. Somewhere in that hillside there is a single specific rock sample, with a physical marker literally bolted into the stone, declaring this exact point the internationally agreed beginning of the Triassic period. It is without exaggeration one of the strangest landmarks on the entire planet, and almost nobody outside a small circle of geologists has ever heard of it. Layered into that same hillside, sandwiched directly between the fossils, are thin bands of ash, carried across an entire ocean from the eruptions we already spent time with. Bed after bed of it stacked through the rock like tally marks. And if you trace your finger upward through those layers in order, something becomes very hard to miss. The fossils get thinner, sparser. Then for a while they very nearly stop appearing altogether right around the exact same layers where the ash bands are packed in tightest together. You do not need a science degree to follow a story like that. You can practically feel where it is going before anyone tells you. What the actual laboratory work eventually pinned down using the same kind of precise radioactive dating we talked about earlier is almost unsettling in how specific it manages to be. The main pulse of extinction, the very worst stretch of this entire event, appears to have unfolded across somewhere in the neighbourhood of 60,000 years. Some estimates stretch that window nearer to 100,000. Researchers still argue over the exact edges of it, the way any honest field of science should, but even the more generous end of that range is by any planetary standard breathtakingly short. Try holding that number for a second, because on its own it can be difficult to feel. Human civilization, agriculture, cities, writing empires, every single one of our wars and inventions and love songs, all of it fits inside roughly 12,000 years. The entire span of everything we consider human history could have played out 5 separate times over back-to-back inside the window. This extinction needed to nearly empty out the ocean. And it still counts in the language of geology as an event that happened almost overnight. Every pyramid, every symphony, every war we have fought, and every peace treaty we eventually signed to end one, every language ever spoken, and every single person who has ever spoken it. All of that history repeated 5 times over, and the planet would still file what happened here under fast. Here's a question worth sitting with for a moment. If you had to watch something collapse, would you rather it happen all at once in a single unmistakable moment, or slowly enough that you kept being able to tell yourself, it might still turn around, I ask, because the ocean in this particular case did not really get either version cleanly. It got something stranger, and I would argue worse than both, because the carbon did not arrive in one clean surge either. The chemical signature locked into these rocks a subtle shift in the very structure of carbon atoms preserved inside ancient shells, and sediment tells researchers not just how much carbon entered the air and ocean, but roughly how quickly. And what that signature shows is a story in 2 acts, not one. First came a slower, gentler rise stretched across thousands of years, the kind of increase an ocean this size can mostly absorb, without anything catastrophic happening right away. Chemistry has some given it. Life has some given it too. For a while the system bent without breaking. Think of it a little like a long relationship absorbing one difficult year without falling apart. People are remarkably good at that. A rough patch here, a hard season there, and somehow the whole thing keeps standing, mostly because there was enough goodwill banked up beforehand to spend a little of it down without the foundation actually cracking. Then came the second wave, sharper, faster, considerably larger than the first, and this time the ocean's usual give ran out. Researchers who study the layered rock from this window can actually see the ocean's chemistry crack under the strain, almost like watching a graph snap in a completely different direction. All within a stretch of time some studies place it somewhere around 20,000 years, a figure that still sounds enormous to a human ear and is once again almost nothing at all to a planet. To put that window beside something you can actually hold in your head 20,000 years ago, there was no agriculture anywhere on this planet, no cities, no written word of any kind. Human beings were small scattered bands of hunters waiting out the tail end of an ice age with absolutely no way of knowing that one day a species like theirs would dig up rock old enough to tell a story like this one. I think there is something worth learning from that two-act structure honestly beyond the raw geology of it. The first pulse was survivable, rough, uncomfortable, but survivable. It was the second one arriving before anything had time to recover from the first that turned discomfort into collapse. Nature, it seems, can often absorb one hard blow. What it struggles with is a second hard blow, landing before the bruise from the first one has even finished forming. Have you ever noticed that pattern in your own life, even at a much smaller scale? It is rarely the first setback that actually takes a person down. It is the second one showing up while you're still catching your breath from the first that tends to do the real damage. This ocean, in its own strange way, was going through something not so different, just stretched across a scale of time no single life could ever have witnessed from start to finish. Now it would be easy to walk away from a story like this picturing a single dramatic afternoon, the ground splitting the ocean, instantly transforming every creature dropping at once in some sweeping cinematic instant. That is not remotely what happened here, and I think it is worth being honest about that, even though the honest version is in its own way far more disturbing than the dramatic one. Nobody standing on that reef would have experienced a single unforgettable day. What they would have experienced generation after generation is a world that kept quietly failing to go back to normal. Slightly warmer summers that never fully cooled again, fewer fish in a particular cove one year, and then the year after that and the year after that. A crinoid bed that used to stretch twice as far as it does now, though nobody left alive would have any memory of it stretching that far to begin with because the ones who might have remembered were already gone. Small forgettable disappointments stacking up far too slowly for any one creature to notice the pattern, yet far too quickly on a planetary clock for anything to actually adapt to it. Evolution is remarkable at handling slow change. Species shift their behavior, their range, their diet, sometimes their entire body shape given enough generations to work with. What evolution has never been particularly good at in any chapter of this planet's story is being handed 60,000 years to solve a problem that would normally take 5 million. If it helps to picture it in more familiar terms, imagine being told your household budget needs to be rebuilt from scratch. Not over the 10 or 15 years a normal life might allow for that kind of adjustment, but by tomorrow afternoon. Nature does not do well with deadlines like that either. Nothing alive on that reef had ever been asked to adapt on a timeline this unreasonable, because nothing alive on Earth in its entire history up to that point ever really had been. And I want to be fair to the science here too, because certainty is not really the mood of this particular chapter. Researchers still debate the exact shape of both pulses, whether there were 2 distinct waves or something more like 3, whether certain regions felt the second pulse slightly before or after others. The broad strokes are agreed upon. The fine detail is still being argued over in journals the way good science tends to keep arguing over its own fine details, long after the headline conclusion has already been settled. What is not seriously in question anymore is the direction all of this was pointing. Carbon dioxide, along with the sulfur and the strange chlorine-laced gases we talked about before, was no longer just sitting in the air above Siberia. It had made its way into the entire atmosphere, and from there steadily into the ocean itself, dissolving into the very water, our crinoids swayed in the very water that trilobite had spent its entire unremarkable life quietly sifting through. And once that much carbon dioxide dissolves into that much ocean, something specific and fairly predictable starts to happen to the water's basic chemistry, something we will get into properly in a moment. But before we get there is a simpler, more immediate consequence worth sitting with first, because it is the one that would have been the easiest of all for anything alive back then to actually feel. All that gas trapped in the atmosphere does something else too. Something far more familiar to anyone who has ever stepped outside under a heavy overcast sky in the middle of summer, the kind of sky that seems to press heat back down onto you instead of letting it drift away. It holds heat in. Multiply that single overcast afternoon by 20,000 years, spread it across an entire planet already leaning toward warmth, and you start to get some sense of where this story is headed next. An ocean that had already lost a good deal of its shallow living space, already lost a meaningful share of its circulation, was about to discover exactly how much heat a trapped atmosphere can hold on to, and exactly how little warning a reef gets before the water around it stops feeling like home. The answer, it turns out, is written into the teeth of that same tiny creature we met a little earlier, the one small enough to sit on the tip of a finger, the one that ended up marking the official end of an entire geological period. Remember the conodont. That strange eel-shaped animal whose fossil teeth quietly decided where one chapter of Earth's story stopped and another one began. It turns out those same little teeth had already been keeping a second secret the whole time, one scientist would not manage to unlock for years after they first started using this creature as a timestamp. Every mineral those teeth were built from formed directly out of the surrounding seawater, and the chemistry locked inside that mineral depends in a small but measurable way on how warm or cool the water happened to be the moment it formed. Water carries two slightly different versions of oxygen inside it, one a touch heavier than the other, and the ratio between them shifts depending on temperature in a pattern reliable enough that researchers can run it backward like a recipe and pull an actual number out of a fossil that has been sitting in solid rock for 250 million years. In plain terms, this tiny extinct creature was without knowing it, quietly building a thermometer out of its own mouth, and then obligingly dying in exactly the right conditions to preserve the reading for a couple of scientists with a rock saw, 2 tons of limestone, and an enormous amount of patience to eventually dig up and translate. It sounds almost too strange to be real. A fossil tooth doubling as a thermometer left switched on for 250 million years. But this is honestly one of the more elegant tricks in all of paleontology, not far in spirit. From the way scientists study a tree's growth, rings to work out which years brought drought and which years brought rain. Except here the pattern being studied is written into the ratio of 2 nearly identical atoms, patiently waiting inside solid stone for someone clever enough to ask the right question of it. Picture that job for a moment too, because it is far less glamorous than the eventual headline made it sound. Somewhere in southern China, a small team spent stretches of time hauling limestone block by heavy block out of exposed rock faces, loading roughly 2 tons of it altogether into crates bound for a laboratory thousands of miles away, all in pursuit of fossils most people would need a magnifying lens just to notice in the first place. Science, more often than the documentaries tend to let on, looks a great deal like manual labour performed in service of a very good question. And when a research team finally did the math on a large collection of these fossils hauled out of southern China, the number they arrived at was startling enough to make headlines well outside the world of geology. Equatorial sea surface temperatures, the study found, may have climbed past 104 degrees Fahrenheit. On land, conditions were almost certainly worse, with some estimates stretching past 120, possibly even 140 degrees, in the harshest stretches of the supercontinent's interior. Without an ocean nearby to soften the swing between day and night, the way coastlines generally do, the deep interior of that single vast continent, likely baked under conditions one of the geologists behind this research openly described as almost impossible for most life to tolerate for any real stretch of time. Ever tried to picture what a single brutal heat wave lasting for thousands of years, running without one meaningful break, would actually do to a landscape? Most of us can barely make it through one bad week of summer heat without complaining about it well into autumn. Plant life in these interior regions would have struggled just as badly as anything struggling in the water. Without consistent rainfall reaching that far inland, and with heat this extreme baking away whatever moisture the soil managed to hold onto entire stretches of the supercontinent's centre, may have supported barely more vegetation than a true desert does today. A striking contrast to the lush, fern-covered coastline we started this whole story standing beside. Sit with that for a second, because a number that size can slide right past you if you are not paying attention. For comparison, the warmest patches of open ocean anywhere near the equator today generally sit somewhere between the high 70s and mid-80s Fahrenheit. Warm, certainly. Pleasant even if you happen to be on vacation. What these researchers were describing was water running a full 20 degrees hotter than that sustained not for one unusual afternoon, but as something resembling the new normal across an enormous stretch of ocean for an uncomfortably long stretch of time. Here is where I will admit something a little embarrassing. When I first sat down to write this particular chapter, I kept getting stuck on one word, because it is the exact word sitting in this video's own title, and I did not want to reach for it too cheaply. But there is honestly no better way to describe an ocean sitting at 104 degrees than this. For a horrifying stretch of Earth's history, a meaningful portion of this planet's tropical waters were functioning as something disturbingly similar to an actual hot tub minus the jets, minus the ability to ever climb back out. Except a hot tub is something you step into voluntarily for 20 minutes before climbing out to cool back down. Nothing living in this ocean had that option. This was not a spa treatment. It was the entire permanent operating temperature of the only home any of these creatures had. It is worth noting too, for the sake of accuracy, that an actual hot tub rarely gets pushed past about 104 degrees Fahrenheit itself, for exactly the reason you would expect. Anything hotter starts becoming dangerous even for a fully grown adult human being dropping in for a few relaxed minutes on purpose. This ocean sat at that same threshold or worse as its everyday baseline condition for thousands of years at a stretch. Now, why does a jump like that matter so much biologically speaking? It helps to think about your own body for a moment. A fever of 104 degrees Fahrenheit in a human being is not a mild inconvenience you shake off with some rest and a tall glass of water. It is a genuine medical emergency, the kind of number that gets you rushed to an emergency room because proteins inside your own cells begin losing their shape at temperatures not far above that. And once a protein loses its shape, it generally stops doing its job. Nearly everything alive in this ocean was in that sense running a permanent planet-wide fever, with absolutely no ice pack, no medication, and nowhere cooler to retreat to. Doctors will tell you the real danger is rarely about the number itself, but about how long a body sits at that number. A brief spike is frightening, but often survivable. A sustained one held for hours instead of minutes starts shutting down the very systems keeping a person alive. Now stretch that same principle across not hours but generations, and you begin to understand why so much of this ocean simply could not hang on. And heat did not just attack these creatures directly either. It attacked the water's ability to support them in a second, sneakier way too, one that connects directly back to something we touched on earlier in this story. Warmer water simply cannot hold as much dissolved oxygen as cooler water can, the same reason a warm soda goes flat faster than a cold one, losing its fizz because gas slips out of warm liquid far more easily than it does out of cold liquid. So picture the trap these creatures were caught inside for a moment. Heat drives up an animal's metabolism, meaning it suddenly needs more oxygen, just to keep functioning normally the exact same way your own body demands more air when you run instead of walk. At precisely the same moment that warmer water was holding on to noticeably less oxygen than before, more demand, less supply, both problems arriving together from the exact same cause with nothing available to soften either side of that equation. It is a little like being handed a marathon to run at the exact moment someone quietly swaps your full tank of air for a thin, restricted breathing tube, and then almost as an afterthought cranks the treadmill's speed up higher still. Nobody finishes a race run under those conditions. Most competitors never even make it particularly far into one. I don't think there is a tidier definition of a trap than that, honestly. Two doors slamming shut from opposite directions at exactly the same time for exactly the same reason. The consequences, once researchers started studying the fossil record from this window of time in real detail, were about as stark as consequences get. Across the equatorial belt of this ancient ocean, fish all but disappeared from the record for an extended stretch. Reef-building algae that depended on stable moderate conditions collapsed. What managed to hang on tended to be small, tough, unremarkable creatures, exactly the kind of organisms built to shrug off a crisis rather than thrive during a golden age holding on in the shallows, while almost everything more particular about its surroundings quietly failed around it. Here's a question worth turning over for a moment. If you had to guess before hearing any of this whether the deadliest stretch of this catastrophe was a story about the world getting suddenly cold and dark, the way it famously did for the dinosaurs many millions of years later, or a story about the world getting almost unbearably hot, which one would you have assumed? Most people I have mentioned this to guess cold, probably because that is the extinction story most of us grew up hearing about first. This one runs almost entirely in the opposite direction. There is something almost unfair about that, if I am being honest. The ending most of us already know, cold and darkness following an impact from space, at least offers a kind of clean, dramatic villain sudden enough to make sense of as a single, unforgettable moment. This ending offers no such mercy. Just water doing exactly what water is supposed to do when you keep adding heat to it, for longer than anything alive at the time had ever been built to endure. I do want to be fair to the ongoing scientific conversation here too, because this particular temperature reconstruction has not gone completely unchallenged. A handful of researchers have pushed back on some of the finer details in the years since questioning whether every single data point was placed in exactly the correct order along the timeline, and whether the sharpest spikes in temperature line up quite as neatly with the worst of the extinction as the original study proposed. That kind of pushback is not a scandal. It is simply how good science is supposed to work, one paper checking another paper's homework sometimes for years afterward. But even accounting for that back and forth, nobody seriously disputes the broader shape of the story anymore. The world got brutally, dangerously hot, and it stayed that way for an uncomfortably long stretch of time afterward. Long enough, in fact, that recovery itself became its own kind of casualty. A thread we will have every reason to pull on properly a little further along in this story. Back on our reef, none of this would have arrived as a single unbearable afternoon, either the same way nothing else in this story has arrived as a single unbearable afternoon. It would have crept in across generations, degree by degree, until one day the crinoids that once swayed so easily in that current were struggling through water that no longer moved quite the same way, thickened and starved of the oxygen it used to carry so easily, and the trilobite sifting its patch of sand was working twice as hard for half the air it had always taken entirely for granted. For now, though, let's bring this back down to the water itself, because heat was never going to be the only thing dissolving into this ocean. Somewhere in all that warming seawater, another quieter transformation was already underway, one that had nothing to do with temperature directly, and everything to do with what all that gas pouring out of Siberia was doing to the basic chemistry of the water itself. Heat can cook a creature slowly. This next part works differently. This next part goes after the very shells and skeletons holding these animals together in the first place. If you have ever dropped a piece of chalk into a cup of vinegar just to watch what happens, you have already seen a smaller, gentler version of exactly what was about to happen to this entire ocean. The chalk fizzes. Tiny bubbles crawl up its sides. Over the following few minutes, the whole piece slowly softens, shrinks, and eventually falls apart into nothing dissolved directly into the liquid around it. Give it long enough, and there is nothing left in that cup but a slightly cloudy liquid, and a faint chalky residue at the bottom, no trace remaining of the solid, dependable little stick that went in at the start. That is not some strange party trick. That is simple chemistry. The same chemistry a classroom teacher somewhere is probably demonstrating to a room full of restless students at this very moment. Chalk is built from calcium carbonate. So is an eggshell. And so, as it happens, is nearly every shell and skeleton that had ever existed in the ocean up to this point in Earth's story. Carbon dioxide, once it dissolves into water, does not sit there quietly minding its own business. It reacts with the water around it and formed a mild acid, the exact same acid in a slightly different concentration that gives soda its sharp bite, and occasionally gives a person heartburn after one too many glasses of it. Pour enough carbon dioxide into an ocean sustained over a long enough stretch of time, and you're not simply warming that water anymore. You're quietly turning it into something not far off from a very large, very dilute cup of vinegar, patiently working on every piece of chalk floating around inside it. There is a slightly more technical piece to this worth understanding too, because it explains why the danger here runs deeper than simple dissolving. Building a shell or a skeleton out of calcium carbonate requires a steady supply of a particular building block floating loose in seawater, something chemists call a carbonate ion. Add enough carbon dioxide to the water, and that same acid reaction starts gobbling up the very carbonate ions a creature needs to build within the first place, well before anything visibly starts dissolving. It is a little like trying to raise a brick wall, while someone quietly hauls away your bricks faster than you can stack them, long before you ever notice the wall itself beginning to crumble. And an awful lot of this particular ocean by this point in its story was built out of chalk in one form or another. Now, for a long time, this part of the story existed mostly as an educated guess. Researchers understood the chemistry perfectly well in theory, the same way you understand that dropping a full glass would probably break it, without necessarily having a recording of the exact moment it happened. What they lacked for years was a way to reach directly into ancient seawater itself and measure how acidic it had actually become rather than simply inferring it from what died. That changed with a rock formation tucked into the Musandam Peninsula, a rugged mountainous finger of land jutting out from the United Arab Emirates, in a spot called Wadi B. It is an unassuming place by most accounts, sun-bleached limestone cliffs rising out of a landscape that looks on the surface like nothing more than desert and old stone. Nobody driving past it would guess they were looking at one of the most important chemical archives connected to the worst event in the history of life on this planet. Buried in the layered carbonate rock there, researchers found something remarkable. A chemical signature written into the element boron locked inside ancient shells that responds to the acidity of the water. Those shells formed in a way scientists can actually measure and translate back into an honest number. For the first time, this gave researchers something much nearer to a direct reading of the ocean's acidity during this crisis, rather than an educated guess pieced together from what happened to survive it. And the story that Boron told lined up almost eerily well with a pattern we've already spent some time with earlier in this video. Remember that first gentler wave of carbon entering the atmosphere followed later, by a second much sharper one. The ocean's acidity followed that exact same rhythm, just written in a different chemical language. During the first wave, the water's pH held its ground reasonably well, absorbing the blow without collapsing. During the second, faster pulse, that resistance simply gave out, and the ocean's chemistry swung hard and fast in a direction that made building or maintaining a shell dramatically more difficult, sometimes almost impossible. Here's a question worth sitting with for a second. Have you ever tried to build something delicate in the middle of an earthquake that is roughly the position every shelled creature in this ocean found itself in during this stretch of Earth's history, trying to construct and repair its own body out of a material the surrounding water had quietly started dissolving faster than it could be replaced? And unlike an actual earthquake, which at least has the decency to eventually stop this particular tremor, kept going day after day for generation after generation, long enough that entire family lines never got the chance to know what a stable ocean floor had ever felt like beneath them. A young brachiopod settling onto the seabed for the very first time had no memory of anything gentler to compare this to. As far as it would ever know, this unstable, corrosive water was simply what an ocean was. It is worth pointing out, too, that not every shell in this ocean was equally doomed, because the chemistry here has an honestly interesting wrinkle to it. One most retellings of this story skip past entirely. Calcium carbonate, it turns out, does not come in just one form. It crystallizes into at least two distinct structures. Chemists call them aragonite and calcite, built from the exact same raw ingredients, but arranged at the microscopic level in slightly different patterns, the way graphite and diamond are technically both built from carbon, arranged so differently that one ends up soft enough to write with, and the other ends up nearly impossible to scratch. Aragonite, as it happens, dissolves considerably more easily in acidic water than calcite does. Many corals, for instance, along with a large share of mollusks, tend to lean on aragonite. A good number of algae, along with plenty of other invertebrates, lean on calcite instead. Two creatures could have been sitting side by side on the exact same patch of seafloor, breathing the exact same increasingly hostile water, and still ended up facing wildly different odds of survival based on nothing more than which of these two nearly identical minerals their particular family line happened to build with. Ever wonder why some ancient shells you might spot in a museum case look impossibly delicate, while others from that same rough era look practically indestructible? There is a real chemical reason behind that difference, and now you know a piece of it. Creatures that had purely by evolutionary accident settled on aragonite as their building material of choice were, without knowing it, standing on far shakier ground the moment this crisis began than creatures who had settled on calcite instead. I find that detail almost unbearably poignant, honestly, once you actually sit with it. None of these animals had any say in which mineral their ancestors happened to land on millions of years earlier, for reasons that had nothing whatsoever to do with a future ocean chemistry crisis nobody could have possibly predicted. It was an entirely arbitrary inheritance, a coin flip made by evolution long before the stakes of that particular coin flip became clear. And when the crisis finally arrived, that ancient arbitrary choice quietly decided who got a fighting chance and who did not. Isn't that how a lot of real disasters actually work, if you think about it? Rarely does a crisis punish the reckless and spare the careful in any tidy, satisfying way. More often, it exploits whatever old forgotten decision happens to be sitting in exactly the wrong place when the moment finally arrives, a decision nobody involved even remembers making. Reef builders, sponges especially, along with a wide range of shelled invertebrates that leaned heavily on the more vulnerable of these two mineral forms, took the harshest end of this particular blow. We will spend proper time later in this story counting exactly who did and did not make it through, so I will not get ahead of myself here. For now it is enough to say that an ocean already running a dangerous fever had just discovered a second entirely separate way to turn against nearly everything sharing its water. Back on the reef we started this story beside that shift would not have announced itself with any single dramatic event either. It would have shown up as brachiopod shells growing thinner than they used to, a little more fragile at the edges with each passing generation, or as a crinoid stalk snapping under a current, it would have shrugged off easily only a few thousand years earlier. Small quiet failures, the kind that never make it into one dramatic photograph, but that add up patiently into something far more like catastrophe than anyone standing near enough to notice would have wanted to admit. I do want to stay honest about the edges of this science too, the way I have tried to throughout this story. Not every researcher agrees on exactly how much of the extinction can be pinned specifically on acidification, as opposed to heat or suffocation, or the handful of other mechanisms stacking up alongside it during this same narrow window. The fossil evidence for acidification in particular can be difficult to separate cleanly from the fossil evidence for everything else happening at the exact same time, since a dissolved shell, and a shell that simply never got the chance to form in the first place, can end up looking remarkably similar by the time a geologist finds it millions of years later. This is very much still an active, occasionally contested corner of the research, not a settled and filed away chapter of the textbook. What is not seriously contested, though, is the underlying chemistry itself, and the fact that it was very much in motion during exactly the window that mattered most. It is strange and more than a little sobering to realize that researchers studying ancient rock and researchers studying today's oceans keep bumping into each other in the exact same chemical territory, using remarkably similar tools to ask remarkably similar questions about remarkably similar numbers. Researchers today, for what it is worth, have already photographed the shells of small modern sea creatures called pteropods, sometimes nicknamed sea butterflies, visibly pitted and thinning in water that has grown more acidic within a single human lifetime. I am not going to pretend that one detail proves history is repeating itself. I am simply going to say it is a strange thing to notice, and leave it sitting there for now. That comparison deserves more room than I can properly give it here, and we will come back to it more carefully before this story is finished. For the moment, I only want to plant the thought quietly and let it sit in the back of your mind the way a low hum sits in the back of a room until you finally notice it, because heat had already turned this ocean into something like a permanent fever, and acid had just begun quietly dismantling its architecture from the inside out, one carbonate ion at a time. And even that combination, brutal as it already sounds, was not yet the full weight of what this water was about to lose. Somewhere beneath the warm, increasingly hostile surface in the deeper, darker water, this story has not spent much time in, yet something else was quietly running out. There was still the small matter of this ocean forgetting how to breathe. Most of us assume an ocean simply has oxygen in it the same automatic way we assume a room has air in it. You do not usually stop to ask where the air in your bedroom actually comes from. It is just there quietly doing its job. An ocean, it turns out, works nothing like that. Oxygen has to travel to get where it is needed, and travel, as we are about to find out, is exactly what this particular ocean had just lost the ability to do. Here is the part of ocean chemistry most people never get taught because most people never have a reason to ask. Warm water is lighter than cold water, not by a huge amount, but by enough to matter enormously over a large enough body of water. And when you heat the surface of an ocean the way this one had just been heated, that warm surface layer starts floating on top of the cooler, heavier water underneath it. The same basic principle that keeps oil sitting on top of vinegar in a salad dressing bottle, refusing to blend no matter how hard you shake it. Under ordinary circumstances, an ocean does not stay so neatly divided. Storms churn it. Currents fold it over on itself. Cold water sinks near the poles and creeps along the seafloor, eventually resurfacing somewhere else entirely, carrying fresh oxygen with it the whole way. That constant folding and resurfacing is in a very real sense how an ocean breathes. Think of it a little like opening a window in a stuffy room. You do not need a hurricane blowing through to feel the difference, just a steady, patient exchange of stale air for fresh. Repeated often enough that the room never gets the chance to properly suffocate. An ocean depends on an equivalent kind of exchange just measured in centuries instead of minutes, and powered by temperature and salt instead of a breeze. Warm this system up enough, though, and that folding motion slows down, then largely stops. The layers set like a drink that refuses to mix, and once that happens, the oxygen sitting in the deeper water has nowhere new to come from, while the oxygen sitting in the warm surface water has nowhere to go except right back into the same thin layer it started in. Meanwhile, deep in that cut-off lower layer, ordinary decomposition never takes a day off. Dead organic matter drifting down from above gets broken down by bacteria the exact same way it always has, and that process consumes oxygen steadily, the way a candle consumes the air trapped inside a sealed jar. Normally fresh oxygen arrives before the supply runs dangerously low. This time, with the usual delivery system switched off, it simply did not. Piece by piece, an expanding pocket of the ocean stopped being able to support anything that needed to breathe at all. Scientists have a specific word for water that has lost its oxygen this way. They call it anoxic. And for a while, that alone might have been survivable in places the way a fish can sometimes limp along in a badly oxygen-starved pond, miserable, but not immediately doomed. What actually turned this into a true catastrophe was the next stage, the one that gives this particular condition its far more sinister name, euxenia. Once oxygen disappears entirely from a body of water, a different kind of microbe tends to take over the job of breaking down organic matter, one that does not need oxygen to survive, and that produces something considerably nastier as a byproduct: hydrogen sulfide. The same compound responsible for that unmistakable rotten egg smell, except here produced in quantities enormous enough to make the water itself actively toxic, not just empty of air. That alone would have been bad enough quietly confined to the deep dark water most sunlight never reaches anyway. Except it did not stay confined. Here's a question worth sitting with for a moment. What do you picture when you imagine the most dangerous water in an ocean? My guess is you picture somewhere deep and lightless, some crushing trench far below where anything with lungs would ever have reason to go. For most of Earth's history, that guess would be correct. During this particular stretch of it, the guess falls apart completely. Researchers studying rock from this exact window, in time, kept finding an extremely specific, extremely strange chemical signature, the leftover pigment molecules from a group of bacteria with one of the oddest lifestyles in the entire natural world. These particular microbes photosynthesize using sunlight for energy, the same way a plant does, except instead of using water, the way ordinary plants do, they run entirely on hydrogen sulfide instead. It is one of the strangest job descriptions in all of biology. Honestly, an organism that treats one of the most famously unpleasant smells most of us know, the reek of a broken sewer line or a forgotten carton of eggs left too long in a warm car as its entire source of fuel. Under ordinary circumstances, these bacteria spend their strange narrow existence crammed into a thin, almost imperceptible band deep inside a small handful of the planet's most oxygen-starved lakes, and inlets a niche so specific and so restrictive that most of us will go our entire time on this Earth without ever having a reason to learn they exist at all. Which means finding their pigments preserved in ancient rock tells you something very specific and very alarming. Sunlight and toxic oxygen-free water were both present in the exact same place at the exact same time. In other words, the poison had not stayed politely confined to the depths. It had risen layer by layer all the way up into the sunlit water near the surface. The very same water that had always up to this point in the ocean's entire multi-billion-year history functioned as its one reliably safe zone. I don't think I can overstate how strange that detail actually is once you sit with it properly. Imagine discovering that the smoke from a house fire had somehow made its way into the one room of the house everyone always assumed was safest, the room people ran toward during every other kind of emergency. That is roughly the scale of the reversal we're talking about here. The surface of this ocean, the shallow sunlit water, where the vast majority of everything alive actually made its home, had quietly become one of the more dangerous places a creature could be. There is a second smaller piece of physical evidence backing all of this up too, one I find almost charming in how mundane it sounds for something so consequential. Buried in this same rock are tiny mineral spheres called pyrite framboids, invisible to the naked eye, no larger across than the width of a human hair, and it turns out their size alone tells geologists something useful. Framboids that form quickly in water, almost completely stripped of oxygen, tend to come out small and tightly clustered. Framboids that form slowly in healthier, better oxygenated water tend to grow larger and more scattered. Geologists can quite literally measure thousands of these microscopic spheres under a microscope, plot their sizes on a graph, and translate that graph into how badly a particular pocket of ancient ocean was struggling to breathe the same way a doctor might check a patient's vital signs off a chart. It is a strangely satisfying kind of detective work, honestly piecing together the health of an entire vanished ocean from spheres too small to see without serious magnification, and I have a soft spot for any science that manages to be that quietly stubborn about extracting a story from something so tiny. Between the bacterial pigments and these tiny mineral spheres, researchers working on sections of this boundary all over the world, from the deep basins of southern China to sections as far away as Greenland, kept arriving at the same uncomfortable conclusion. This was not a localized problem. Pockets of toxic, suffocating water were showing up in ocean sediments, an enormous distance apart from each other, suggesting something far more like a widespread, creeping condition than an isolated bad patch of seafloor. If it helps to have something familiar to compare this to, we are not actually short of modern examples. Every summer, a stretch of water off the coast of the United States out in the Gulf of Mexico quietly turns into what oceanographers now casually refer to as a dead zone water, so starved of oxygen that fish, shrimp, and crabs either flee it entirely or do not survive the encounter. The trigger today is different. Mostly fertilizer runoff feeding explosive blooms of algae, rather than ancient volcanic warming, but the basic physics underneath it, oxygen consumed faster than it can be replaced, layered water refusing to mix, is not so far removed from what this much older ocean was contending with, just at a scale almost impossible to comfortably picture. I want to be careful not to overstate that comparison, because the causes honestly differ, and I try not to flatten two different stories into one just because they happen to rhyme in places. But the basic physical experience of being a creature caught inside a dead zone wherever and whenever it happens to occur does not seem to change very much across 250 million years. Water without air is water without air no matter what century or period or epoch happens to be sitting on the calendar at the time, Have you ever swum in water that just felt wrong somehow, too warm, too still without being able to say exactly why? That instinct is older than most of us realize, and in this particular ocean, it would not have been wrong. Back on our reef, this would have arrived exactly the way everything else in this story has arrived so far. Not as a single dramatic afternoon, but as a slow tightening generation after generation, as the safe, breathable margin of water these creatures had always relied on quietly shrank from somewhere far below into somewhere uncomfortably near, and then in places into somewhere it had no business being at all. And here is the part that should honestly unsettle you, if the rest of this has not already managed to. Every single mechanism we have walked through so far in this story, the heat, the acid, and now this has been happening at the exact same time, layered directly on top of one another in the exact same stretch of water. This was never a story about one crisis. It was always a story about several arriving together, each one making the others considerably harder to survive. I keep coming back to that idea, honestly, because it feels like the real lesson buried underneath all the chemistry. A single disaster, no matter how severe, tends to leave a door open somewhere. Enough survivors slip through, enough habitat holds, and life finds its way back eventually. What this ocean was facing instead was a set of doors slamming shut in careful overlapping sequence, each one sealing off whatever narrow escape the last one might have still allowed. And even that combination was still missing one final, particularly cruel twist, because all that trapped hydrogen sulfide sitting in the water was not going to stay in the water either. It was about to rise straight up out of the ocean entirely, and into the one place none of these creatures had ever needed to worry about before the sky itself. Gas trapped under pressure in a liquid does not stay trapped forever. Anyone who has ever shaken a bottle of soda and then made the mistake of opening it too quickly already understands this in their bones, even if they have never once thought about it in scientific terms. Eventually that gas finds its way to the surface and it comes out. Anyone unlucky enough to have actually made that particular mistake also remembers the mess that follows sticky liquid spraying across a kitchen counter, because pressure that has been quietly building somewhere for who knows how long does not politely ask permission before it finds a way out. What had been quietly building inside the deeper oxygen-starved layers of this ocean, all the hydrogen sulfide produced by microbes doing the only kind of breathing still available to them, was never going to stay politely dissolved forever either. As those toxic layers pressed nearer the surface, and in places broke through it entirely, that gas finally had somewhere new to go. Up, out of the water, into the one part of this story that had up until now remained almost entirely untouched by anything happening below the waves. It is worth remembering that we're not talking about some small contained leak here either. We spent real time earlier discovering just how widespread this toxic water had already become, stretching across ocean basins thousands of miles apart. Multiply that scale by all the centuries this condition persisted, and you begin to understand that what eventually broke the surface was never going to be a modest amount of gas. Before we follow it up there, it is worth understanding exactly what this particular gas does to a living creature, because it is nastier and considerably more specific than most people assume. You already know the smell even if you have never known its name. That unmistakable rotten egg odour drifting up from a clogged drain or a forgotten carton, left too long in a warm refrigerator, is hydrogen sulfide announcing itself in tiny, mostly harmless quantities. In small doses it is simply unpleasant. In larger ones it stops being a smell you notice, and starts being a poison your body cannot ignore. There is something almost funny about that in a dark sort of way, that one of the deadliest agents in the history of this planet announces itself with a smell most of us associate with a forgotten gym bag, or a neglected refrigerator, rather than anything that sounds remotely dangerous. Nature rarely bothers to make its worst threats sound impressive in advance. Here is the part that honestly surprised me when I first looked into the chemistry properly. Hydrogen sulfide does not kill the way drowning kills by denying a creature oxygen outright. It works far more like the way a much more infamous poison works. At high enough concentrations, hydrogen sulfide interferes directly with the tiny machinery inside a cell responsible for actually using oxygen, jamming the exact same biochemical gears that a substance like cyanide jams. A creature poisoned this way can be surrounded by perfectly breathable air and still suffocate because the problem was never a shortage of oxygen reaching the body. The problem is a body that has suddenly lost the ability to use the oxygen it already has. Sit with that distinction for a second because I think it matters. This was not simply an ocean running short of air. In places it was an ocean actively poisoning anything that tried to breathe inside it, whether or not there happened to be enough oxygen sitting right there for the taking. It is an unsettling category of poison, honestly precisely because it defeats the very instinct that usually saves a creature's life in an emergency. Every animal alive knows on some deep wordless level to swim for the surface to claw for open air the moment it senses it cannot breathe. That instinct is built entirely around one assumption, that fresh air once reached will actually solve the problem. Hydrogen sulfide breaks that assumption completely. A creature could reach the surface. It could fill its lungs with perfectly good air. And it would not matter because the failure was never happening in the lungs to begin with. Now back to that gas finally breaking the surface and rising into open sky. A researcher named Lee Kump, working out of Pennsylvania State University, put forward an idea in the early 2000s that took this story somewhere even stranger than the ocean itself. Kump was not a biologist chasing a dramatic headline for what it is worth. He was a geochemist, the kind of researcher who spends most of a career patiently balancing equations about sulfur and oxygen, and rarely expects any of it to end up told as a bedtime story 2 decades later. But every so often, patient chemistry produces a conclusion strange enough to escape the journals entirely and land in rooms like this one. His argument ran roughly like this: once enough hydrogen sulfide escaped into the atmosphere, it would not simply drift around causing localized trouble near the coastline. It would climb high enough to start interacting with the ozone layer, the thin, fragile band of gas wrapped around this entire planet that quietly absorbs the harshest of the sun's ultraviolet radiation before it ever reaches the ground. Think of the ozone layer a little like sunscreen for an entire world invisible, easy to take completely for granted, doing its job so quietly that nobody thinks about it until the day it stops working. Kump's argument was that hydrogen sulfide in large enough quantities could rip holes in that protection, allowing a flood of ultraviolet radiation to reach the surface of the planet in a way it normally never would. Without that shield, the same ultraviolet light responsible for an ordinary sunburn on an afternoon at the beach would arrive at an intensity capable of damaging the genetic material inside a living cell, directly quietly scrambling the very instructions a plant or an animal needs to grow correctly, to reproduce correctly, to simply keep functioning the way it is supposed to. And this is where the story briefly leaves the ocean altogether, because the evidence researchers eventually went looking for was not sitting in seawater at all. It was sitting inside fossilized pollen. A researcher named Henk Fischer, working out of Utrecht University along with several colleagues, began examining ancient plant spores from right around this exact window in time and found something strange. A noticeably high number of them were malformed, misshapen in ways healthy spores from other periods generally are not. The primary explanation on offer was startlingly specific. This is roughly the kind of damage you would expect to see if these plants had spent a stretch of their existence being bombarded with far more ultraviolet radiation than any plant is built to tolerate. Picture a scientist hunched over a microscope somewhere looking at pollen grains barely visible to the naked eye and slowly piecing together evidence for a hole in the sky that sealed itself back up 250 million years before anyone was born to witness it directly. There is something almost unbearably moving about that, to me at least. An entire planetary wound diagnosed centuries later from scars left behind in something as small and as easily overlooked as a single grain of pollen. Have you ever looked hard at something impossibly small, a fingerprint, a single strand of hair, and realized it was quietly holding an entire story inside it? Paleobotanists, it turns out, get that feeling professionally on a fairly regular basis. Here's a question worth turning over for a moment. How much of the worst damage in any disaster do you think actually gets left behind in the small, unglamorous details nobody thought to protect at the time? We tend to imagine catastrophe leaving behind craters and ruins. More often, it seems catastrophe leaves its clearest fingerprints in the smallest, most forgettable places, the ones nobody was paying attention to until long after the fact. Now, I promised earlier in this story that I would stay honest about the edges of the science whenever they got a little blurry, and this particular chapter has some real blur to it, more than most of what we've covered so far. Not every researcher who has modelled this scenario agrees that hydrogen sulfide alone was capable of doing the kind of damage Kump originally proposed. Later atmospheric studies running more detailed chemical simulations have argued that the ozone layer may have proven considerably more resilient than his original hypothesis, assumed even under fairly extreme hydrogen sulfide loads. Some of those researchers suggest the deformed pollen might trace back to a different cause entirely, perhaps ordinary environmental stress unrelated to ultraviolet exposure, rather than a genuine hole torn into the planet's ozone shield. I want to be upfront about that disagreement rather than smoothing it over for the sake of a tidier story, because I think the honest version is actually more interesting than the tidy one. Science at its best looks exactly like this one clever, well-reasoned idea, followed by other researchers stress-testing it from every possible angle, sometimes for decades before anyone gets to call the question settled. Whatever the final verdict on the ozone layer specifically turns out to be, the direct cyanide-like toxicity of hydrogen sulfide itself is not seriously in dispute. That part of the danger was real, whether or not the sky above it was also quietly failing at the exact same time. I find a strange kind of comfort in that ongoing argument. Honestly, the same comfort I find whenever a mystery refuses to wrap itself up too neatly. A field of study still actively arguing about its own conclusions is a field of study still paying proper attention, still refusing to settle for an answer, just because that answer happens to be dramatic and convenient. Given the choice, I would rather sit with an honest maybe than a tidy answer, built on more confidence than the evidence actually earns. And here is a detail worth sitting with before we move on, because it reshapes how you should be picturing everything we have covered across this entire video so far. None of this, the heat, the acid, the suffocation, the poison gas ever respected the line between ocean and shore. Air does not know where a coastline ends. Whatever was rising out of this water was rising into the same sky, sitting over every dry breathing creature on the only continent this planet had at the time. The ferns and early conifers we passed on that first quiet morning, the reptiles hunting insects near those old worn-down mountains up north. All of it was breathing the same increasingly hostile atmosphere this ocean had just finished poisoning. This was never only a story about a suffering sea, it just happens to be the version of the story we've chosen to follow most carefully tonight. We've now walked through nearly every mechanism this catastrophe had in its arsenal. The heat that turned the water into something resembling a permanent fever. The acid that dissolved the very material holding shells and skeletons together. The suffocation that stole the air out from under everything that needed it. and now poison gas potentially clawing away at the one shield standing between every living thing on this planet and the raw, unfiltered edge of the sun itself. It is time, I think, to stop describing the weapons and start counting exactly what they did. Numbers this large tend to slide right past a person unless you slow down and actually sit with them one at a time, so that is exactly what we're going to do for the next few minutes. Not one giant abstract statistic, a roll call. Name by name, group by group, exactly the way you would go through a list at a memorial, because that is honestly not far from what this is. Before we get there, a quick word on the numbers themselves, because good science rarely hands you one clean figure and asks you to trust it blindly. Researchers measure a loss like this in a few different ways, sometimes counting individual species, sometimes counting whole, genera the broader family grouping species belong to, and sometimes counting families themselves. Those different counting methods produce somewhat different percentages, and depending on which paper you happen to be holding, you will see numbers ranging from the high 80s into the high 90s. I am going to use the figure most commonly cited for a marine species as a whole, somewhere in the neighbourhood of 96%, while staying honest that the exact decimal shifts a little, depending on how narrowly or broadly a researcher chooses to count. Now the roll call. Remember that trilobite we spent a morning with sifting patiently through the sand, the last of a dynasty that had already been crawling across ocean floors for nearly 300 million years, reduced by this point to only a couple of surviving species anywhere on the planet. Both of those species died. Every single trilobite left on Earth gone, ending one of the longest unbroken success stories evolution had ever produced right at the exact moment this story reaches its worst chapter. There would never be another one. Not next year, not next epoch, not ever again for the rest of Earth's history. That patient armoured hunter we noticed tucked into a crack in the rock, the one people sometimes call a sea scorpion, despite it being no true scorpion at all, its entire family line went extinct as well. An animal lineage old enough to have watched trilobites rise to power in the first place did not manage to outlast them by even a single geological heartbeat. The reef itself, the low uneven wall of stone and life we open this story standing beside, did not survive intact either. The corals holding that structure together, the specific rugose and tabulate varieties that had spent tens of millions of years quietly building reefs across this ocean, disappeared completely, not thinned out, not reduced to a struggling remnant somewhere. Gone every last one, taking an entire architectural style of reef building, down with them one this planet would not see again in quite the same form for millions of years afterward. Picture a city losing not just its residents but its actual architects, the specific builders who knew how to raise its buildings in the first place, with nobody left, who remembered the technique well enough to start over. That is roughly what happened to reef building itself during this particular window of time. The knowledge, so to speak, did not simply pause. It had to be reinvented from scratch by entirely different organisms a very long time later. The blastoid's small flower-shaped relatives of starfish and sea urchins that had decorated seafloors for longer than most people would ever guess, vanished completely as well, ending their own branch of the evolutionary tree for good. And those countless fusulinids drifting through the water in numbers too enormous to properly count. The ones we joked earlier had accidentally built themselves the most understated retirement plan in the history of life, built entirely out of the limestone cliffs their own shells would one day become. Roughly 97% of their diversity disappeared as well. Their legacy survived them by hundreds of millions of years preserved in solid rock. The organisms themselves did not get nearly that lucky. Brachiopods, the reliable, unglamorous shellfish carpeting seafloors across this entire ocean, lost somewhere around 96% of their diversity too, an entire dominant group reduced to the barest whisper of what it had been only a short while earlier. A few lineages clung on, but the version of this ocean built around brachiopods as one of its central load-bearing groups effectively ended here. Crinoids, those swaying feathery gardens we spent so much time admiring at the very beginning of this story, fared almost as badly, losing somewhere around 98% of their diversity in this same narrow window. A handful of hardy lineages survived thin threads, holding an entire group together by little more than luck and stubbornness. But the lush, dense meadows we described at the start of this video would not exist again in anything like that form for longer than most of us can comfortably picture. Ammonoids, those coiled jet-propelled hunters drifting above the reef, took a brutal hit too, somewhere around 97% of their diversity gone. The particular style of ammonoid most common during this era did not make it through at all. What did survive was a single narrow branch barely hanging on, that would eventually go on to produce the far more familiar, far more successful ammonites of later chapters. In Earth's story, a reminder that survival sometimes comes down to one thin, unglamorous thread nobody would have bet on at the time: gastropods. The broad group we would recognize today as sea snails lost somewhere near 98% of their diversity in this same narrow window. Radiolarians, tiny glass-shelled plankton drifting invisibly through open water, suffered losses even higher than that, quietly erasing an entire tier of ocean life, too small for any of us to ever have noticed with the naked eye, yet fundamental to feeding almost everything larger than itself. And that shark we watched cruising past the reef with such unbothered confidence, it made it. Sharks as a group came through this catastrophe considerably better than almost anything else we have spent time with tonight, adding one more entry to a survival record that by this point in Earth's history was already remarkably long. I like sitting with that detail for a moment, honestly, because this entire story has been so relentlessly heavy that a single real survival feels earned rather than cheap. Not every character in this particular story ends the same way. Have you ever wondered why sharks get called living fossils so often in nature documentaries and museum placards alike? Now you have at least part of the answer. Bivalves, the broad group that includes clams, mussels, and their many relatives, also came through in noticeably better shape than almost anything else in this roll call, losing somewhere in the range of 60 to 65% of their diversity at the genus level, brutal by any ordinary standard and yet remarkably survivable compared to the near-total wipeouts we just walked through. So why bivalves? Why sharks? What did they have that trilobites, corals, and countless brachiopods simply did not? Researchers who have dug into this question have found a fascinating pattern, one that goes deeper than simple luck. It comes down in large part to blood chemistry of all things. Animals equipped with efficient specialized proteins for carrying oxygen through their bodies, the kind found in the blood of bivalves, of many mollusks, of fish, including sharks, held a real measurable advantage over animals that depended on oxygen, simply diffusing passively through their tissue, the way corals and many brachiopods largely do. In a world where oxygen itself had become the scarcest resource in the entire ocean, having a more efficient internal delivery system for whatever oxygen remained turned out to matter enormously. Think of it a little like the difference between a delivery service running dedicated trucks straight to your front door and a delivery service that simply drops your package somewhere in the general neighborhood and hopes it eventually finds its way to you. Both systems work fine when supply is abundant and nobody is in a hurry. The moment supply turns scarce, only one of those two systems keeps functioning reliably. It is a strange thing to realize, honestly, that something as invisible as blood chemistry, a trait these animals had carried for entirely unrelated reasons for millions of years beforehand, quietly became one of the deciding factors in who got to keep existing and who did not. On land, the story was brutal in its own way too, though we are focusing most of our attention on the ocean tonight. Roughly 70% of vertebrate genera living on that single supercontinent disappeared during this same stretch of time. Apex predators, among them animals that had ruled the top of their food chains for millions of years, gone in the same narrow window that emptied out the sea. Here's a question worth sitting with for a moment. When most people picture the deadliest extinction in this planet's history, what actually comes to mind first? My honest guess is dinosaurs, a falling asteroid, that unmistakable image most of us grew up seeing in documentaries and museum dioramas. I want to gently correct that assumption because it matters here. The event that eventually wiped out the dinosaurs happened around 66 million years ago, and by most careful estimates, it took something in the neighborhood of 75% of species with it. A real catastrophe by any measure, the kind that rightly earned itself an entire genre of documentaries and museum exhibits. What we have been walking through together across this entire video happened almost 200 million years earlier than that at a point in Earth's story, when dinosaurs did not exist yet in any form. Not a single one. They would not show up on this planet for another 20 million years or more after the events of tonight's story had already finished playing out. And this earlier catastrophe, the one far less likely to show up in a museum gift shop or on a lunchbox or in a summer blockbuster, was worse. Considerably worse by nearly every honest measure researchers have managed to put together. If 96% still feels like an abstract number, rather than something you can actually picture, try this instead. Imagine walking through your own hometown, every street you've ever known, every building, every familiar face, and being told that only 4 out of every 100 of those buildings would still be standing by the time you reach the other side of town. Your childhood home gone, the corner store gone, the school, the park, the place you had your first job, all of it gone, not relocated, not rebuilt somewhere else nearby. Simply erased from the map entirely, as though none of it had ever been built in the first place, and the only proof any of it existed is a handful of photographs nobody left behind to develop. That is roughly the scale of erasure we're talking about here, just applied to an entire ocean's worth of living things instead of a single town. We have spent this whole video walking through exactly how this happened, the heat, the acid, the suffocation, the poison rising into the sky. Now we know exactly what it cost. What we have not yet asked is the question sitting right on the other side of that number. Because 4% small as it sounds is not zero. Something made it through, and what made it through has one of the strangest, most improbable stories in the entire history of life on this planet. Survival, as it turns out, rarely looks the way we expect it to look. We tend to picture the toughest, fiercest, most impressive creature standing tall over the wreckage, the undisputed champion of a brutal contest. What actually made it through this particular catastrophe looked almost nothing like that. It looked honestly a little ridiculous. Picture something roughly the size of a large pig low to the ground, with a stocky barrel-shaped body built for digging rather than fighting. Its face carries a short, blunt beak instead of a full mouth of teeth, and on either side of that beak sit 2 stubby tusks useful for rooting through soil and stripping tough vegetation rather than hunting anything down. Early paleontologists who first pieced this creature together from fossilized bone looked at that broad shovel-shaped skull and decided the most fitting name they could give it translated roughly meant shovel lizard. Not fearsome, not majestic, practical in the most literal sense a name can be. This is Lystrosaurus, and it is about to become, for a stretch of Earth's history, one of the single most successful land animals this planet has ever produced. If you're picturing something between a bulldog and a very determined pig, you are honestly not too far off. It stood low, moved with a waddling, businesslike gait, and had absolutely nothing about it that suggests it ever won a staring contest with anything more intimidating than a fern. And that, as we're about to see, turned out to be a considerable advantage. Here is the number that stopped me cold the first time I came across it properly. In certain rock layers from right after this catastrophe, particularly in a stretch of South Africa, researchers called the Karoo Basin paleontologists have found that somewhere around 95% of all land vertebrate fossils recovered belong to this one single genus. Not 95% of one species among many living comfortably alongside each other. 95% of everything walking on four legs across that entire landscape was for a while essentially the same animal over and over again as far as the fossil record can tell. Try picturing an entire town where 19 out of every 20 people you passed on the street happen to share the exact same last name, and you start to get some sense of how strange that statistic actually is. Researchers use a specific term for a creature that dominates a landscape this thoroughly in the immediate aftermath of a catastrophe. They call it a disaster taxon, an opportunistic survivor that floods into space left wide open once its usual competitors and predators have been cleared away. It is not glamorous. It is not really a victory in any heroic sense. It is far more like what happens when a single hardy weed takes over an entire abandoned lot, not because it beat anything in a fair fight, but because almost everything else that might have challenged it simply was not there anymore. Have you ever driven through a town after a major flood or wildfire and noticed how quickly certain plants, usually the toughest, least remarkable ones, seem to reclaim the bare ground before anything else even has a chance? That is roughly what an entire continent looked like, biologically speaking, in the years following this catastrophe. Not a triumphant return to normal, a weed taking hold in the cracks because the cracks were finally empty enough to take. So why Lystrosaurus out of everything alive at the time? A few traits appear to have mattered enormously. It burrowed digging shelters underground that would have offered real protection from the punishing surface heat we spent time with earlier in this story. It ate an unusually broad range of tough, low-quality plant material rather than depending on any one specific food source, which matters enormously when the usual menu has just been devastated. And with most of the large predators capable of threatening a fully grown adult wiped out alongside everything else, there was for a while almost nothing left standing in its way. None of that sounds like the plot of an adventure story. It sounds more like a very good, very boring risk management plan, and I think that might be exactly the point. Catastrophes rarely reward the flashiest competitor in the room. They tend to reward whichever competitor had the fewest ways left to fail. Here's a detail that still gives me a small thrill every time I think about it properly. Fossils of this exact same genus have turned up not only in South Africa, but in Antarctica, in India, in Russia, in China, scattered across landmasses that today sit separated by entire oceans. For a long time that distribution puzzled naturalists enormously, until the pieces finally clicked into place alongside everything else we now understand about Pangaea. A single, unremarkable burrowing herbivore wandering freely across one unbroken supercontinent ended up becoming one of the more convincing pieces of physical evidence that these separated continents were ever joined together at all. It is a strange kind of legacy for an animal nobody would have called impressive while it was alive. Now, I promised earlier in this story to stay honest about the rougher edges of the science, and this particular chapter has a truly interesting one worth including. Not every researcher today is convinced Lystrosaurus actually deserves the disaster taxon label in the first place. A detailed review published in 2020 took a much harder look at exactly when different Lystrosaurus species appeared and diversified relative to the extinction itself, and argued that the timing does not cleanly match the strict definition researchers use for a true disaster, taxing an opportunist that specifically blooms in the immediate aftermath of a crisis. Some of its success, this newer argument suggests, may simply reflect a creature that was already reasonably well positioned before the catastrophe ever struck, rather than one that rose from nothing purely because the field had been cleared. I find that kind of correction quietly reassuring, if I am honest. It means researchers are still willing to walk back even their most famous, most frequently repeated stories, once better evidence shows up, rather than protecting a good narrative simply because it has already made it into textbooks and documentaries. Even the survivors of this catastrophe, it turns out, get their stories double-checked, revised, occasionally taken apart and rebuilt. There is a second correction worth mentioning, too smaller but equally telling. For years, some researchers pictured Lystrosaurus splashing around in rivers and shallow water, a little like a modern hippopotamus, based on the general shape of its skull and body. More recent studies examining the fine internal structure of its bones under magnification have leaned back toward a fully land-based lifestyle, instead an animal built for digging through soil rather than paddling through water. Even the basic question of where an animal spent its days, it turns out, can take decades of careful, unglamorous work to properly settle. There is a second, much smaller kind of survivor worth mentioning too, one that left behind an entirely different sort of fossil evidence. Right around this same window in time, sediment layers all over the planet show an enormous spike in fungal spores, far more than any ordinary period of Earth's history typically produces. Researchers studying this spike have generally interpreted it as a grim kind of good news for fungi and terrible news for everything else. Forests in staggering numbers had died. Where forests die, wood rots, and where wood rots, fungus thrives, blooming across a landscape of dead and dying trees, stretched across an almost unimaginable portion of the planet's surface. Have you ever noticed how the aftermath of any disaster always seems to have its own particular set of opportunists, the businesses or organisms perfectly positioned to profit, while everything around them struggles? This fungal bloom might be the oldest example of that pattern we have any physical evidence for at all. Even the ocean had its own strange equivalent of Lystrosaurus in a sense, though we have not had the chance to properly mention it until now. With the reef-building corals we said goodbye to earlier, completely gone from large stretches of ocean floor, something far older and far simpler quietly moved back into the space they left behind, mats of microbes, similar in spirit to some of the very first complex life forms this planet ever produced, building layered mineral structures, researchers now sometimes call disaster forms, precisely because they only really flourish once everything more sophisticated has been cleared out of their way. It is almost as though the ocean stripped down to its studs briefly reverted to a much older version of itself, one from hundreds of millions of years earlier, before reefs as we would recognize them had even been invented. Picture an elegant, well-appointed house burning down, and in the empty lot where it used to stand, someone eventually throws up the simplest possible shelter, imaginable, 4 walls and a roof. Nothing decorative about it, just enough to keep the rain out, until something better can eventually be built again. That is roughly what these microbial mats represented for an ocean that had for the time being lost the far more elaborate architecture it once relied on. One last thread worth pulling on here because it connects back to something we touched on only briefly earlier in this story. Many of the creatures that did survive this catastrophe came through noticeably smaller than their relatives had been beforehand, a well-documented pattern researchers call the Lilliput effect. For years, the standard explanation was straightforward. Smaller bodies need less food, less oxygen, and generally handle hostile conditions more easily than larger ones. so evolution simply favoured the little guy. More recent, more careful research has complicated that tidy story somewhat, suggesting that at least part of this apparent shrinking might actually reflect enormous numbers of young, not yet fully grown animals dying before they ever reached adult size, skewing the fossil record toward looking smaller overall, rather than every surviving lineage truly evolving to be permanently tinier. Both explanations may well be true simultaneously, working alongside each other, and researchers are still sorting out exactly how much weight to give each one. I want to leave you with something before we move forward, because I think it is the real emotional centre of this entire chapter. Not one of the creatures we've discussed in this section survived this catastrophe by being remarkable. Lystrosaurus was not fast or fierce or clever in any way earlier generations would have singled out as special. It simply dug a hole at what was available and kept doing that day after day through conditions that had already erased 96% of everything sharing the ocean with it. If there is a lesson buried inside that, and I think there might be, it has very little to do with strength and quite a lot to do with stubbornness. We spend so much of our own time on this earth, I think, assuming that surviving something difficult requires being exceptional. This particular chapter of Earth's history quietly argues otherwise. Sometimes the whole trick is simply refusing to stop showing up one unremarkable day after another, until enough of those days finally add up to something that looks from a great enough distance like success. But making it through the worst of the killing was never going to be the end of this story either. Surviving a catastrophe and inheriting a world worth surviving for turned out to be two very different things, and the world these creatures had just fought so hard to remain part of was about to make that distinction painfully clear. Here is something most retellings of this story leave out entirely, mostly because it does not offer the tidy, hopeful ending we tend to want from a disaster story. Once the worst of the killing finally slowed down, this planet did not simply dust itself off and get back to business. It spent millions of years stuck in a kind of stalled, unfinished recovery, near enough to healed that you might have mistaken it for progress, far enough from actually healed that almost nothing could take root and stay there. Picture convalescing from a serious illness only to discover that every time you finally start feeling strong enough to stand, something knocks you flat again. Not quite back to where you started, but nowhere near actually well either. That roughly is the shape of the next several million years of this story. We already spent time with the reason the tropics in particular struggled so badly. That punishing heat we walked through earlier, water pushing past 104 degrees Fahrenheit at the surface, did not politely disappear once the extinction itself wound down. Researchers studying this window estimate that the hottest stretch of ocean on the entire planet remained essentially uninhabitable for something in the neighbourhood of 5 million years, a tropical dead zone sitting right in the part of the world that should under ordinary circumstances have been the richest, most crowded real estate the ocean had to offer. 5 million years is an almost impossible span to hold in your head properly, so let's try building it out of something smaller. If you imagine one single generation of a brief marine creature lasting about a year, 5 million years works out to 5 million consecutive generations existing and dying, and never once getting to experience a tropical ocean that behaved the way a tropical ocean is supposed to behave. Or picture it a different way. 5 million years ago on our own far more recent timeline, our most distant ancestors had not yet learned to walk upright the way we do now. That is roughly the depth of time we're talking about here, except instead of describing the slow climb of a single lineage towards something new. This stretch describes an entire tropical ocean, sitting essentially empty, waiting for conditions to finally settle down, enough to let anything meaningful move back in. Here's a phrase worth learning tonight because I think it might be the single most quietly devastating idea in this entire story. Researchers have a name for a group of creatures that technically survives a mass extinction, checking every box you would use to call something a survivor, and then goes extinct anyway, not immediately but slowly over the following few million years, worn down by conditions that never actually let up long enough for real recovery to take hold. They call this a dead clade walking. Sit with that phrase for a moment. A dead clade walking. A lineage that crossed the finish line of the worst part of the catastrophe that appeared in every meaningful sense to have made it, and then quietly, unglamorously finished dying anyway years later, once nobody was paying near enough attention to notice the exact moment it happened. Survival, it turns out, is not always a single yes or no question answered once and settled forever. Sometimes it is a temporary reprieve dressed up to look like an ending. Picture a group of creatures that technically checked every box during our roll call a little earlier present, and accounted for in the fossil record right after the crisis, seemingly carrying their lineage forward into this new damaged world. And then a few million years later, without any single dramatic event marking the moment that same lineage simply stops appearing in the rock entirely. No fanfare, no second catastrophe with a name attached to it. Just a slow fade into a silence nobody was positioned to notice happening in real time. I find that idea almost unbearably sad, if I am honest, more than almost anything else we have covered across this entire video. A monster arriving all at once and taking everything in a single blow is horrible, but at least it is finished quickly. A slow, grinding erosion that convinces you the worst is over right before it finishes the job anyway feels like a crueler kind of ending altogether. Now let's talk about coal, because the story hiding inside this one particular rock tells you almost everything you need to know about how thoroughly this recovery stalled out. Coal forms from thick waterlogged accumulations of dead plant material, compressed and preserved over enormous stretches of time in swamps and peat bogs. It is in a very real sense a direct physical record of healthy functioning wetland ecosystems successfully doing their job for millions of years running. And for a stretch of roughly 10 million years immediately following this catastrophe, geologists have never found a single meaningful coal deposit anywhere on the entire planet. Not a thin seam, not a partial layer. Essentially nothing across the whole world for 10 million consecutive years. Researchers eventually traced the reason back to the plants themselves. The specific species responsible for building healthy peat swamps before the crisis had been wiped out along with almost everything else, and the wetlands left behind afterward turned notably more acidic and hostile than they had been before. It took roughly 10 million years for a new generation of peat-forming plants to evolve enough tolerance for these harsher conditions to get the whole system running again. Not 10 million years for plants in general to return. 10 million years specifically for this one particular ecological function, turning dead vegetation into durable peat to come back online anywhere on Earth. Try to picture what that actually looked like on the ground across a hiatus that long. Swamp still existed, rain still fell, plants in some diminished form still grew back, but the specific patient slow-motion process of building up thick, healthy peat, the same kind of ancient material that eventually compresses into coal and quietly powers a meaningful share of human civilization, many millions of years later, simply would not take hold anywhere on the planet for a stretch of time longer than separates us today from the first apes that ever stood upright on two legs. Have you ever noticed how much easier it is to break something in a single afternoon than to properly rebuild it, even with every resource in the world sitting right there available to you? Multiply that imbalance by several million years, and you start to understand the shape of this particular chapter. Have you ever tried rebuilding a habit or a system after everything supporting it fell apart all at once, only to discover the rebuilding takes considerably longer than the falling apart ever did. This is roughly that same principle, just stretched across a timescale that makes any human comparison feel almost embarrassingly small. The ocean's own version of this delay ran on a strikingly similar schedule. Remember those disaster forms we mentioned, the simple microbial mats that quietly moved into the empty space left behind once the reef-building corals disappeared? That stopgap arrangement did not resolve itself quickly either. Researchers tracking the planet's carbon cycle through this period have found it stayed truly unstable for at least 5 million years into the aftermath, swinging through repeated disruptions rather than settling calmly back into balance. And even once that instability finally calmed down, coral reef diversity itself took roughly another 6 million years after that to climb back to anything resembling its pre-crisis richness. Add that up and you are looking at something in the neighbourhood of 10 million years start to finish before this ocean's reefs looked anything like reefs again. I want to underline something in that timeline because it is easy to skim past. This was not one clean crisis followed by one clean recovery, the tidy shape we tend to assume disasters take. The carbon cycle kept lurching through repeated additional disruptions throughout this entire stretch. Aftershock after aftershock, each new wobble undermining whatever fragile progress the previous few 100,000 years had managed to build. Ecosystems would begin creeping back towards something stable, only to have the ground shift again before they finish the job. It reminds me a little of watching someone repaint a room, only to have a new leak spring from the ceiling every time the last coat finally dries. Eventually the room gets painted. It just takes considerably longer and costs considerably more than anyone standing there with a paintbrush on day one would have ever guessed. If that sounds familiar in a strange, quiet way to anyone who's ever tried to recover from something truly difficult in their own life, I don't think that is a coincidence worth ignoring. We tend to imagine healing as a straight upward line, each day a little better than the one before it, right up until you're simply better. Real recovery in a person, or in an entire planet, rarely seems to work that way. It happens in fits and relapses, 2 steps of real progress, followed by 1 step sliding back for far longer than anyone involved would have liked or expected going in. Most other mass extinctions in Earth's long history, severe as they were, tended to see meaningful ecological recovery within a handful of million years. This one took roughly twice that by some of the more conservative estimates researchers have put together, which is part of why paleontologists so often treat it as being in a category of its own, not simply the largest mass extinction on record, but also one of the slowest to truly let go of the world it had already broken. If this planet ever filled out a performance review for itself after this particular chapter, eventually recovers, though timeline management could use significant improvement, feels like a fairly accurate summary. We have now walked through nearly the entire arc of this story together. A quiet reef, a hidden trap in the shape of a continent, a sleeping giant waking beneath Siberia, 20,000 years of carbon pouring into the sky, an ocean turning first into something like a fever, then into something like acid, then into something that had simply forgotten how to breathe, and finally 96% of everything gone with the stubborn, unremarkable 4% left to somehow rebuild a broken world across the following 10 million years. That is a great deal of time and a great deal of loss to have carried across a single evening together. There is only one honest question left standing at the end of a story this large, and it is not really about the past at all anymore. It is a question about right now, about the ocean sitting outside your window this very evening, whether you happen to reside near one or not, because every ocean on this planet is in the end the same connected body of water we've been telling stories about all night. The water lapping against a pier somewhere on a coast you've never visited is chemically, physically, unmistakably the same ocean that once boiled a trilobite's home into something unrecognizable. Researchers who study ancient ocean chemistry keep circling back to this particular event over and over for a very specific reason. When they compare the rate at which carbon entered this ancient ocean, the same 20,000-year surge we spent real time with earlier tonight, against the rate at which carbon is entering today's ocean through entirely different means, human industry, rather than buried coal seams cooking under Siberian lava, the two numbers land near enough together to make more than one careful scientist visibly uncomfortable in an interview. Some research even suggests the modern rate may be moving faster than the ancient one did, condensed into a window of mere centuries rather than tens of thousands of years. I want to be careful with that comparison the same way I have tried to be careful with every comparison across this entire story. The mechanisms are not identical. The starting conditions of the ocean, the surrounding biology, the timescales involved, all differ in real meaningful ways, and any honest scientist studying this question will tell you plainly that ancient rock can only ever offer an imperfect mirror, not a prophecy. Nobody serious is claiming history is guaranteed to repeat itself line for line, but a mirror, even an imperfect one, is still worth looking into occasionally. Remember those small, delicate sea creatures we mentioned briefly earlier, the ones nicknamed sea butterflies. Researchers monitoring today's oceans have already photographed their shells, thinning and pitting in water that has grown measurably more acidic. Within a single human lifetime, the same basic chemistry we spent an entire chapter walking through tonight, just playing out over years instead of tens of thousands of them. I am not going to tell you what to make of that. I only promised earlier in this story that I would come back to it properly, and I did not want to leave that particular promise unfinished. What this ancient ocean tells us more than any single number ever could is what tends to happen when a great deal of carbon enters seawater considerably faster than that water's own chemistry can quietly absorb it. Heat climbs, acidity rises, oxygen thins out in exactly the places most living things depend on it most. None of that is speculation about the future. It is simply a description of something that has already happened once recorded patiently in rock boron, and the teeth of a creature that stopped existing 250 million years ago. Geologists studying this ancient chemistry have another phrase they sometimes use almost clinically for what happens once carbonate becomes scarce enough in seawater. An ocean's capacity to support a shell or a skeleton simply stops being guaranteed. It becomes instead a question the water itself gets to answer, one organism at a time, the same brutal negotiation we watched play out across an entire ocean 250 million years ago. Do you think a species alive 250 million years from now, looking back at rock laid down during our own lifetime, would find a story worth telling? I like to imagine they would, and I hope whatever they end up writing turns out a little kinder than this one has. I will leave the conclusions from that comparison in your hands rather than mine, because I think you are entirely capable of drawing your own, and because a bedtime story is honestly not the place for me to lecture you about anything. I only wanted you to know the comparison exists clearly enough to think about it later on your own terms whenever you happen to be ready to. There is a gentler thread running through this story too, one I would rather leave you with as we finish up tonight, because I think it deserves the last word more than any warning does. Death in the strange accounting of deep time tends to create opportunity. Every one of those niches left standing empty once 96% of the ocean and 70% of the land had gone quiet did not stay empty forever. Something eventually moved into every single one of them. A separate branch of reptiles barely noticed during the late Permian quietly began spreading into all that vacant space during the Triassic, that followed, diversifying into forms that would tens of millions of years later produce the dinosaurs. For a while, this newly opened world filled with an almost experimental range of reptiles, trying out every lifestyle available to them, some built for speed across open ground, some adapted for life in shallow coastal water, some eventually taking to the air entirely, the first backboned animals on this planet ever to manage true flight. None of that experimentation would have had anywhere to happen if the world it was filling had not been so thoroughly catastrophically emptied out first, and on a much smaller, much quieter branch of that same family tree, a handful of surviving synapsids, distant cousins of the group Lystrosaurus itself belonged to, held on as well, though not by dominating anything. They survived by shrinking, by going quiet, by becoming small, careful, mostly nocturnal creatures scattered through the undergrowth, while these newly diversifying reptiles took over the daylight world above them. That unglamorous, overlooked lineage hiding through the shadows of an age that did not belong to it would eventually give rise to the very first mammals. That period of hiding, as it turns out, left permanent fingerprints on what a mammal even is. Generations spent operating mostly after dark, while louder, more successful reptiles claimed the daylight hours, appear to have pushed these small ancestors towards sharper. Hearing a keener sense of smell, and eventually fur and adaptation perfectly suited to staying warm through a long night, spent avoiding anything bigger than itself. Every mammal alive today, including the one currently listening to this sentence, may be quietly carrying the inherited habits of an ancestor that spent an entire geological age too sensible to come out from under cover, which means, if you want to trace the thread all the way to its actual end, you sitting here right now watching a video about an ocean that finished dying 250 million years ago exist at all because a small, forgettable creature somewhere in that same wreckage refused to stop existing. Not triumphantly, not dramatically, quietly, patiently, the exact same way Lystrosaurus did, the exact same way almost everything in this story that made it through actually made it through. I keep coming back to that thought more than any other piece of this story, honestly. We tend to imagine ourselves standing at the end of some grand inevitable line humanity, as the intended destination the whole story was quietly building toward. The truth, once you actually follow the thread back through nights like this one, is considerably stranger and considerably more humbling than that. We are here because an obscure, unremarkable animal survived an almost unsurvivable catastrophe by hiding and shrinking and simply refusing to give up on a world that had given it every reason to. There is no version of this story where the outcome felt guaranteed at the time. Millions of years of therapsid dominance ended almost overnight. An entire branch of formerly minor reptiles suddenly handed the whole daylight world to themselves, and somewhere in the gap between those two facts quietly, without any fanfare at all, the ancestors of every mammal that would ever exist, held on by the barest possible margin in the dark, waiting for a world that would not fully belong to them again for well over 100 million years. If there is one thing I hope settles in with you tonight long after you've drifted off, it might be this. The worst catastrophe this planet has ever recorded did not end the story of life on Earth. It rewrote it slowly, painfully, unglamorously over the following 10 million years, and something entirely new eventually grew out of the wreckage it left behind. That does not make the loss we walk through tonight any smaller. 96% is still 96%, and every creature we said goodbye to across this video mattered in its own small particular way, exactly as much as anything living today matters. But endings, even catastrophic ones, have a strange habit of quietly becoming beginnings, too given enough time and enough of that same stubborn refusal to simply stop. If I had to boil an entire evening's worth of volcanic rock boiling seawater and vanish trilobites down into a single idea, it might be this. Nothing about this catastrophe was simple, and nothing about it was quick, and nothing about it followed the kind of clean, single-cause story we usually prefer to tell ourselves about disasters, ancient or otherwise. It was geography, quietly setting a trap, a supercontinent's worth of vulnerability stacked up over millions of years before a single volcano ever erupted. It was heat and acid and suffocation and poison, arriving together rather than one at a time, each one making the others harder to survive. And it was recovery that refused to move in a straight line, stumbling forward for 10 million years before the world finally quietly started to look like itself again. If there is a thread holding every one of those pieces together, I think it is this. Almost nothing about a disaster this size ever comes down to one clean cause or one clean lesson or one clean ending. It comes down to a great many smaller things stacking up quietly long before anyone thought to add them all together. Thank you for spending this evening with me, and with this ancient, overheated, quietly heroic little ocean. Stories like this one take a great deal of care to put together properly, digging through decades of research, just to find the handful of details worth carrying into a room this quiet, and having you here all the way to the end means more than you probably realise. If you made it this far without dozing off somewhere around the acid rain or the ozone layer, consider that a genuine achievement and one this particular narrator is more than a little proud of. If your evening is winding down the way I hope it is, let your eyes rest now. Let the room stay soft and quiet a little longer. There will be another story waiting for you soon, another forgotten corner of this planet's long, strange history, dug up, dusted off, and ready whenever you're ready to come find it again. Sleep well tonight, and I will see you next time.